Great. So yeah, I'm very happy to be here and talk about bosonic error correction beyond topological error correction. So as Norman mentioned, so most of my recent work has been on bosonic quantum computing, and in particular about these Kerr-Cats. And so fortunately or unfortunately, I'm not going to be talking about Kerr-Cats at all today. Depending on the time, we might take it up later. But the main focus is going to be, telling you about what I mean by bosonic qubits, what I mean by bosonic error correction, and why this might be more interesting. The Kerr-Cat qubit is one of the bosonic qubits, for example. But yeah, that's not what I want. That's not what I'll be talking about today. So I've tried to design this lecture to be quite introductory. And my hope is that, we get into more details during the questions. So I encourage you to ask as many questions as you can, and, I'll try to answer everything. And in case I'm unable to answer something, I'll get back to you later and answer that. Okay, so I also wanted to introduce the people who are taking the questions today, the moderators. I have Nick Frattini, who is a graduate student at Yale. He's an experimentalist, and he was the one who demonstrated the Kerr-Cat, for example. And I also have Shraddha, who is my student, and she is actually working on scaling up these bosonic qubits with surface codes, which you learned about from Austin Fowler and John Martinez, I guess. Okay, so let's very quickly, bring your attention to bosonic qubits, because we have been talking about, just your regular, discrete, conventional qubits in the last earlier in the week. So you've learned that in order to make an error correcting code, the idea is that you take many physical qubits to encode one logical qubit, and then you error correct a small subspace of that large Hilbert space that you have created. In case of bosonic qubits, now bosonic qubits are also called as CV qubits, that is continuous variable qubits. And in these qubits, the idea is that these qubits are encoded in some non-classical state of a harmonic oscillator. Now, as you know, the Hilbert space of a harmonic oscillator is in principle infinite. And so you already have a large Hilbert space, and now you can encode a qubit in a subspace of this large Hilbert space and do error correction that way. So there are many types of bosonic qubits. I'll quote some famous ones here. The GKP qubit, which is the Gottesman-Kitaev-Preskill qubit. Then we have the binomial code or binomial qubit. Then we have rotation symmetric. You have Kerr-Cats. You have like a whole bunch of things, cat codes, all of that, right? Okay, so now with conventional qubits, the next the idea behind error correction will be that you look at what are the most likely errors happening in your system. And you correct against those most likely errors. And also another thing that you assume is that the noise is weakly correlated. It's not strongly correlated, because say you build a surface code, and for some reason your noise is that you introduce a bit flip error on all the qubits at the same time, then your error correction is not going to work, right? So you assume that there's only one error at a time, or a few qubits undergo errors at a time, rather than the whole system, just blowing out of your code space. Okay, now in case if on the other side, the CV bosonic qubits, the idea is that you want to correct it against the most likely errors that can happen in a harmonic oscillator. So the errors that we think about here are like, photon loss. For example, you go from higher excited Fock state to a lower energy Fock state. You can have photon gain. You can have frequency fluctuations, and we'll look at examples of this during the course of this lecture. And the reasonable assumption about noise that we make here is that the most common errors are low weight operators. Now, what do I mean by low weight operators? It just means that these operators have only local support on your harmonic oscillator basis state. So, for example, if you're looking at Fock states, then it's very unlikely that you are going to suddenly go from a vacuum state to a 50 photon Fock state. Those errors are very less likely. The more likely errors are, you go from the vacuum state to the 1 photon Fock state, maybe to the 2 photon Fock state, and things like that. So the assumption here is that you have low weight errors. Now, in error correction with conventional qubit, the idea is that you can simply increase the size of your code, and then you can correct for more and more errors. So you looked at, for example, the surface code. So if you have a D by D patch of surface code, then you can correct for D plus 1 over 2 errors in this. So basically, the bigger this lattice you make, the more errors you'll be able to correct. And in this case, that you've learned about surface codes by now, so that the threshold theorem is valid, which means that if each operation in building the surface code of each qubit fails with some probability p, then the probability of logical error goes as p over p threshold to the power of d plus 1 over 2. So basically, as long as your physical error rate is below the threshold error rate, your error correction is going to be successful. All you need to do is just make a bigger and bigger code to correct for more and more errors.
Shruti, there's a comment saying the slides are not readable.
Oh.
Maybe putting the iPad in horizontal mode fixes it.
Oh, there you go. Sorry about that. Okay, fine. I think it's better now. Yeah, good. Yeah. Okay. Okay, so then, so on the right-hand side then, on the left-hand side, we're just adding more qubits to correct for more errors. On the right-hand side, we're going to add more photons. Your code, the size of the code is related to the average photon number in your state, and the bigger state, more photons you add in your code, the more errors you'll be able to correct. And again, we will, understand this aspect more as we go on. On the left-hand side, you can clearly see, in some sense, these qubit-based codes are sort of hardware inefficient because you're using many qubits, and you have to control these many qubits to make one logical qubit. Right. So in the surface code, you have d square qubits, and you use d squared qubits to encode one logical qubit. On the right-hand side, in principle, with the bosonic codes, you can encode a logical qubit inside a single oscillator. So in principle, you can have an n equal to 1, k equal to 1 code, where n equal to 1, k equal to 1 means that you're encoding one logical qubit in one physical oscillator. So in this sense, it's hardware efficient. Now, I've put a fact here that in principle, it's supposed to be hardware efficient. Now, whether in practice it's actually going to be hardware efficient is something that we need to think about. The reason being is that firstly, the error model that here we are assuming that you have low weight errors. Is that really the error model that are the physical systems that are sitting in the lab face? So we'll come to that point in a second. Now, there's another type of bosonic qubits, which I call, these are just sort of Hamiltonian or dissipatively stabilized versions of these bosonic codes, wherein you engineer a Hamiltonian, or you engineer a special dissipative environment such that the errors are sort of autonomously corrected, unlike the kind of qubit codes that you have been learning about so far, where you measure some stabilizers and then go back and correct for them. In case of bosonic codes, we also have, instead of doing this active error correction, there's Hamiltonian or dissipatively stabilized versions of these bosonic codes. In fact, the Kerr-Cat qubit is one such. It comes under what is called as a stabilized cat qubit. It's a category of stabilized cat qubit, and that's a Hamiltonian stabilized version of a bosonic code. But this is not what we will be looking at in this lecture. But just so you know, it's out there. You can take a look at it if you're interested, or we can talk about it later. Okay, so now we come to the most important aspect that I was telling you about before. The most important principle is there's no free lunch. I think that's the most important principle in the world. There is no free lunch. And similarly for these bosonic codes, even though I'm telling you that there are codes which have n equal to k equal to 1, so they're supposed to be very hardware efficient, but in reality, it's very, very hard to actually make these codes work with n equal to k equal to 1. And the reason being is that the actual error model that happens in your oscillators is not low weight errors. This is because when you have an oscillator, when you have a harmonic oscillator, in order to do anything, in order to even create a bosonic qubit in it, you need some external nonlinearity. You need a regular qubit to even create a bosonic qubit. You need a discrete two-level system to even create a bosonic qubit. And when you try to do that, then there can be some errors that the oscillator inherits from the discrete qubit control. And those errors are not low weight errors, those are high weight errors, and that can prevent you from actually making an n equal to 1, k equal to 1 code. This is, again, we will come to this point again, and I'll give you a very specific example of where this happens. And in fact, that specific example it captures everything. This is why that specific example will tell you what is the limitations behind almost every bosonic qubit out there.
Shruti,
yeah.
We have a question asking, like, do we really have that kind of control to sort of be able to engineer the noise part of our Hamiltonian as well?
Yes, we do. That's a fantastic question. We do have the control to be able to engineer the noise part as well. Of course, nothing can be perfectly engineered. So yes, so there's something called as a dissipative cat, where they engineer this particular kind of dissipation, which is called as two-photon dissipation, to create the stabilized cat. And that stabilized cat autonomously corrects for bit flip errors. So suppose I give you qubits, right? And if I tell you, if you have qubits, correct for bit flip errors, only bit flip errors, forget about phase flips, right? If I tell you only correct for bit flip errors, then you'll go and make a repetition code out of it. That's the easiest way to do it. With these dissipative cats or even Kerr cats, you engineer the environment and engineer the Hamiltonian in such a way that you autonomously correct for bit flip errors. There's no feedback and things like that. But yes, in circuit QED, you have this amazing control with you that allows you to do this stuff. Allows you to basically create whatever Hamiltonian and dissipator you want.
Super cool. And I guess two more questions sort of right along that line, which is sort of like, if we have the ability to engineer this, are we correcting errors that are a different type than normal? And again, what exactly does low weight mean? Like, are these errors different, or are they the same types of errors?
We are still correcting for low weight errors. We are still correcting for low weight errors. If you have a very high weight error, you can be, it will ruin your system. But again, the point is that the way those things are engineered, the high weight errors are not present. Are very, very rare. Yeah, sorry, go ahead.
Yeah, sorry, the question was more exactly what does can you define high weight for us?
I will come to that point. Please bear with me. I'll tell you what a high weight error is. This is just an overview, just a taster to tell you what's coming in the future, just to give you an overview. But I'm going to exactly tell you what I mean by a high weight error. So just bear with me. Okay. So let me go on. So what I'm saying right now is that somehow high weight errors can be introduced into the system. Errors that the bosonic code is not designed to correct for can come into the system. And so what now? Then how do we correct for those errors, right? So then the idea is that you basically take your bosonic qubit and just concatenate it with another code which can deal with those high weight errors. So for example, you can take your bosonic qubit and concatenate it with the surface code. That's totally allowed, and there are proposals to do that. That's absolutely, you can do it. But then what is the point of bosonic qubits now, right? Because I'm saying that I like bosonic qubits because they're hardware efficient, but now I'm going to concatenate them to surface code anyway, which is hardware inefficient. So then why do I even care about a bosonic qubit? The idea is that, let's come back to this formula, and this formula basically captures the idea. So remember, in the surface code, the probability for logical error basically goes as P over P threshold to the power of some D plus 1 over 2. The idea is that with bosonic qubits, you can do some degree of error correction locally, right? You just make a bosonic qubit in a single cavity. You just do some local, on the single mode itself, you do some active error correction so that you're basically decreasing this P. So in regular qubits, if P is say 1%, with bosonic qubits, maybe you can take this number to be, 0.01% or something like that because of local error correction. So now when I build the surface code on top of it, I will require much fewer bosonic qubits to build the surface code because I started with a much better, much higher quality qubit in the first place. The other thing that you can do is, so the kind of bosonic qubits that I'm going to talk about today, the idea with them is mainly to decrease this numerator. There's also ideas where you can use the properties of the bosonic qubits to increase the denominator itself. So you can either decrease the numerator or increase the denominator. So for example, with these square-cat qubits, you can make the threshold for the surface code really large. So which means that if you increase the threshold by, say, a factor of 2 or even factor of 5 or 10 or whatever, if you're able to increase the threshold, that means that for the same P, you will now need a smaller distance code to reach the same target logical error rate. So again, you'll need fewer resources to get to the same logical error rate. So this is the point of using bosonic qubits. That even if at the end of the day, you're going to concatenate it with a regular code, you will still need fewer resources overall to implement this concatenated version of the bosonic code. Okay, so this was just an overview, and now we can jump into the details. And again, bear with me, I will come to the point of what these high weight operators are. Are there any questions?
Yeah, Shruti, there's one question which is more general. Maybe it'd be better if you answer it. So why would harmonic oscillators not be considered a conventional qubit candidate? So they've seen discrete qubits so far, and I think this question is along those lines.
Why are they not discrete qubits? Why harmonic oscillators not discrete qubits?
I guess, yes.
Well, so I mean, yeah, you can, at the end of the day, we are encoding a discrete qubit in the harmonic oscillator, but the fact that, when I say discrete qubit, I mean a qubit which has just 2 levels, level 1 and level 2, right? Just 2-level system, an atom, like 2 levels in an atom, that's it. I don't allow myself to go to any other state, there are only 2 states. Now, in bosonic qubits, yes, the qubit that you're encoding is still a 2-level, you still need a 2-dimensional subspace to encode your qubit, but the error correction works because your errors take you, because you have a large Hilbert space, and the errors are actually taking you to these other states, and then you can correct it back and bring it back to your qubit subspace. In a discrete qubit setup, you cannot do that. It's just a 2-level system. You cannot do error correction in a 2-level system. You need a large Hilbert space to do error correction on a subspace. So indeed, we are error correcting a 2-dimensional subspace of this infinite dimensional harmonic oscillator, and therefore they're not really discrete qubits in some sense. Did that answer the question?
Thanks. And there's another question which says, how scalable are 3D cavities? How feasible is it to group a bunch of them and do surface code?
My God, you guys are already jumping so far ahead. Yeah, you can scale them. There's no problem. Nick is sitting here. He's an experimentalist and he thinks you can scale them, so I believe him. But no, you can scale them. There's no problem in scaling them. But you can also do any bosonic qubit in a 2D. Like you can do it on chip. You just need to make good enough cavities, and yes, it's possible to make high Q cavities in 2D as well. So there's nobody is stopping me from building a bosonic qubit in 2D. In fact, the Kirkat qubit, bosonic qubit, is a 2D qubit. It's not living in a 3D cavity. So yeah, if you want to do 3D cavities are scalable. If you want to do 2D cavities, you can also do everything in 2D cavities. No problem with that.
Thanks.
Shruti,
Yeah, go ahead.
Oh, yep. Yeah. So that's, I mean, that's cool. Yeah. So we can make these both in 2D and 3D. And the sort of nagging question then is sort of about if you sort of mentioned that these codes can correct bit flips, but what about correcting phase flips? Are there also bosonic codes that correct phase flips besides just bit flips? And why don't we?
Absolutely. So we will look. So the qubits that we're going to look at today, for example, the GKP qubit, it corrects for all errors. We're going to look at binomial codes which correct for all errors. Those are the two that I'll talk about which correct for all errors. This bit flip was just an example I gave you about the specific example for a Hamiltonian stabilized cat. But yeah. We are going to look at codes which can correct for all errors that can happen in a cavity.
The questions about logical error probability. Is there an intuitive explanation for the d+1/2 error scaling?
Oh, I mean, I don't have an intuitive explanation, but this is just how the surface codes work. So I believe Austin may have talked about this.
Okay. So, and then the next question sort of, I think you've already answered it, says the surface code formula for PL, or does it also hold for bosonic codes? If so, what is D in the bosonic code?
Yeah, it's the same. It's the number of cavities that you're going to have. So basically, I mean, you say you have a surface code patch like this. Right here, you just have, instead of putting, I don't know, your transmon qubit or your trapped ion qubit or whatever your favorite qubit is, you just put cavities. So it's the same thing. So yes, it's the same D that's going to come up there.
Thanks.
Okay, so I think I'm gonna, if there are no.
There are a few questions, but maybe you could go ahead and we throw these questions.
Yeah, I think because I won't be able to finish otherwise. Okay, so I'm gonna go ahead, and please, we'll come back to all of these points and everything will become clear to you just as we go ahead. Okay, so now we're gonna start looking at these codes. The three main codes that I will try to cover today is the binomial code, the CAT code, and the GKP code. I'm going to start with a quick overview about error channels and error correcting criteria in case you missed one of the early lectures. I think Ken Brown talked about this. And then I'm going to tell you how you can encode a qubit in the harmonic oscillator and what are the type of errors that we can happen, that we can get. Also, a disclaimer that in our talk, in this talk, we'll only talk about error correction for building a quantum memory. I'm not going to talk about how you would do all the gates, universal gate set in this system. It's just going down a rabbit hole, which I want to avoid doing here. But again, those are questions that we can take up in the discussion. Okay, so basically we will be looking at the quantum channel formalism. So basically any quantum operation can be written as a linear Krauss map, and the only thing that these Krauss operators MI need to satisfy is that MI dagger MI has to sum to identity. So you must have looked at so far. In case of qubits, you must have looked at a poly error channel where these MIs are the poly operators. So you can have the error channel as with with some probability I rho I happens, with some probability a X rho X happens, some probability Y rho Y happens, and with some probability a Z happens. In case of cavities, the most common error channel is a single photon loss channel, in which M1, you can think about it as the action of the photon annihilation operator with some probability P. And M2, of course, I have to make sure that this condition is satisfied. So of course, I need another cross operator to complete that condition. And I can just complete this condition with this cross operator. So basically, this represents a single photon loss event, single photon loss channel in oscillator. And we can have 2 photon losses, 3 photon losses, and so on. And we'll come to that as we go ahead. Okay, so you also then looked at the error correction criteria. So if you remember, the error correction criteria was that the cross operators must satisfy. So if PC is a projection onto your code space, then you should have MI dagger MJ, PC is AI J PC. Or in other words, if you have your 0 and 1 code words, you basically want to have 0 MI dagger MJ, 0 has to be equal to 1 MI dagger MJ 1. This is the no distortion condition. And then the other condition coming from this guy is then the orthogonality condition, which says this has to be 0. If your channel, the cross operators for your channel satisfy these 2 conditions, then you can do error correction, right? Okay, so now let's look at encoding a qubit in an oscillator. So remember, the Hilbert space of the oscillator can be written in terms of Fock states, right? So you have Fock state 0, Fock state 1, Fock state 2, Fock state 3. So the simplest way to encode a qubit in an oscillator is just using the Fock state 0 and Fock state 1, right? So here, just to make sure, so I'm going to call the qubit state 0 to be the Fock state 0 and qubit state 1 to be the Fock state 1, just to make sure that these are just the Fock states. Okay, so now let's look at what the cross operators do to the.
There's a comment about not scrolling down so quickly, maybe.
Okay, I'll go down slow. Okay, so now, so these are the 2 cross operators that I'm interested in. And in terms of these 2 cross operators, M1 is not going to do anything to my 0 state. I mean, yeah, it's the eigenstate. And then, well, it's going to add 0 times 0, basically. And then M1 acting on the 1 state is just going to give me the 0 state. So basically, I can just take the M1 and M2 operators and project it onto the Fock state basis. And effectively, M1 and M2 can be written as, so M1 can then be written as P0, 1, and M0 can be written as square root of 1 minus P, 1, 1, and I can simplify it as do a little bit more math, and this becomes 0, 0 plus 1 minus P, 1, 1. This is exactly the amplitude damping channel of a qubit, of a regular qubit. So basically, a relaxation event, for example, in a transmon is technically an amplitude damping channel, and these are what the corresponding cross operators are. So,
Shruti, real quick,
yeah.
that M0 there, should it be M2?
Oh, what notation? Yeah, sorry, I used a different notation in my notes, so I
Oh,
messed
yep.
up. Sorry about that.
No
It's
worries.
a good point. This is M2. Yeah. Okay. So this is the amplitude damping channel for a regular qubit. So I don't know if you actually went through this in any of the earlier lectures, but to correct for an amplitude damping channel, you need 5 qubits. So the smallest code which can correct for amplitude damping channel is a 5-qubit code. So if I just was not thinking too much and I just use a Fox state 0 and Fox state 1 of an oscillator to encode my qubit, I'll need 5 such oscillators to correct for single photon loss. I'll basically make an 5-qubit amplitude damping code. It turns out, however, that if you're a bit more clever and you choose your code space a bit more cleverly, you can just use a single oscillator to correct for this single photon loss channel. So let's see what those clever code words are. So you can basically—
Shruti, real quick before we go to those code words, just want to confirm that the A and A dagger that you're using are indeed the same sort of raising and lowering operators of a harmonic oscillator.
Yes, A and A daggers are raising and lowering operators of the harmonic oscillator. Yeah, so A dagger is 1. Okay, so now let's look at a different choice, right? Because you see, as I said before, you have all these different Fox states, and I could use any Fox state to encode the qubit. So I could call the state 0 plus 4 over square root of 2 as my state 0, and 1 to be the Fox state 2. Okay. Maybe I can put a bar here so you don't confuse between Fox states and what are these logical states. Okay, and now let's see if these satisfy the error correction criteria. So to make sure that I don't mess up, I'm gonna copy stuff from my notes here. Okay, so again, M1 is square root of B A, M2 is square root of 1 minus B A dagger A. So if you look at M1 acting on 0 bar, this is just so this is square root of 4 by square root of 2, 3, and then I have M1 acting on 1 bar. This is square root of 2, 1. And then I have M2 acting on 0 bar. This is square root of 1 minus P times 4. Oh, sorry. This should be 0 plus square root of 1 minus 4P, 4 by square root of 2. And if I have M2 acting on 1 bar, this will be square root of 1 minus 2P2. So using these using these transformations, you can check that all the error correction criteria are satisfied. So I don't want to do the math here, but you can, I can post my notes online and then you can even go through the math to convince yourself that this is true. So the error correction criteria is going to be satisfied. You can easily check it. So this means that now I'm able to, I can make an error correcting code that corrects for this single photon loss channel by using this encoding in a single oscillator. I think this is pretty amazing, and this tells you the strength of a harmonic oscillator, that you can make a better code. Otherwise, if you were naive, if you were just using the naive encoding, you would have needed 5 qubits to correct for an amplitude damping channel. But if you were clever, you can now use only 4 levels in an oscillator. So 5 qubits is like a Hilbert space of 2 to the 5, right? So you were using much larger Hilbert space with 5 qubits. Whereas here, you're just using up to 4 levels of your harmonic oscillators. I think this is it's pretty amazing that you can do this. Now, how do you actually perform error correction? I'm going to wait for a second here. Is there any questions on this part? Does anybody want me to go through the math?
I think you're good.
we have a quick question, which doesn't the lowering operator put 0 to 0? Why have you gotten rid of it? Or
Oh
basically,
no, the lowering
why?
operator just doesn't, yeah, it's 0 times 0. So it doesn't do it. So it's 0. It just goes to,
So it
goes
has
away.
eigenvalue 0. So it really like
Yeah,
gets rid of this.
it just gets rid of it. There's no lower eigenvalue than 0 for in harmonic oscillators. That just it just puts an end to it there. Okay. Great. So now how do you actually do error correction in this? So these are so basically there's an error, your M1, okay. So you started with these states, and if there was an error, you either, if there was a loss, if there was a M1 event, then you go to these states, 3 or 1. And if there was an M2 event, you go to these states. So you can only have M1 or you can have M2. That's the only thing that can happen in this system, right? So now what you can do is you measure a stabilizer for this code. A stabilizer for this code is what is the parity operator. And if you actually went through the notes that I posted earlier, the parity operator is this guy over here. Okay, so if you look at it, the code words 0 bar and 1 bar are the +1 eigenstates of the parity operator. So I'm going to write, maybe I can go back to this configuration now, so I don't have to scroll that often. Right, so your code words are 0 bar, 0 plus 4 over square root of 2, 1 bar, which is 2. So if you look at this, the Fock state 0 is a +1 eigenstate of the parity operator. The Fock state 4 is also the +1 eigenstate of the parity operator. So therefore, this superposition state is also the +1 eigenstate of the parity operator. Whereas this guy, the Fox, the state, sorry, and similar, sorry, the state 2 is also +1 eigenspace. So the code space is the +1 eigenspace of the parity operator. But if you have an error, if you have a single photon loss error, then you know that the states that you had was state 3 and state 1, and these are the -1 eigenstates of the parity operator. So P acting on 3 is -3, and P acting on 1 is -1. And similarly, these two states are the +1 eigenstates of the parity operator. So basically what you can do is go and measure parity. You go and measure this guy, and I'll tell you how we're going to measure this guy, but you go and measure this guy. If you know that the parity was, if you get the measurement outcome to be 1, then you know that you actually went to these states, Fox state 3 and Fox state 1, and you can actually apply a unitary operation to bring yourself back into the code space. If you measure that, if you found the parity to be +1, then you know that these guys over M2 is what happened. And then if you know P, then you can apply unitary to again reverse the effect of M2. But to do that, you need to know what P is. And in experiments, we do know what P is. It's related to some physical parameters in your system, so we know what that is. And we can go and apply unitary to recover the state. So basically by measuring parity, we know whether M1 happened or whether M2 happened, and we can apply unitaries to go and recover the state. And this, sorry, let me just finish. And this error correction protocol has been implemented in experiments. Yeah, okay. Maybe I can stop for a second.
A question, is A dagger A under the square root sign?
Yes, it is.
And how do you check the errors without collapsing this? Okay, that's done, sorry. Is that 4 level in an oscillator versus 2 to the 5 qubit levels? And qubits difference lie in the fact that a lot of qubit states have multiple errors which are not correctable?
A lot of qubit states have multiple errors which are not correctable. No, I'm still correcting. I mean, my goal is to still correct for a single amplitude damping error in any one of the qubits. So it's true that now I have 5 qubits, so there's more chances. So I have 5 choose one ways where I can get an amplitude damping error. But it's the same thing in this as well. The probability of an error also increases with the number of Fox states that you have in your code. So it's similar. It's similar thing there. Yeah. I'm not sure how to put. I'm not sure if I have an intuitive explanation for why it works so well with just a single oscillator. I guess the errors just behave nicely compared, yeah, I don't know.
Okay, another question. This is like encoding qubit into a qubit with D equals 5 effectively. Then a subspace of qubit space is the code space? Question mark.
I'm not sure if I understand the question. This is, any error correcting code is encoding a qubit in a like in a larger Hilbert space. Yeah, so this is encoding a smaller Hilbert space into a larger Hilbert space.
Great, thanks.
Okay. So now I want to tell you how you can measure this parity operator, and that is where you will find out what the high weight error is that I was telling you about before. So in order to measure the parity, what you do is you actually require a regular qubit. So in circuit QED, you have a 3D, these experiments were first done in 3D cavities. So you have a 3D cavity in which your bosonic mode sits, your bosonic qubit sits, and then you have a transmon sitting outside, and then you have a dispersive coupling between the harmonic oscillator and a transmon, and you use that to measure parity. Now, the coupling Hamiltonian between these two can be, the dispersive coupling Hamiltonian that I was talking about is this guy here, where A dagger A are the cavity modes, those are the regular bosonic operators, and Z represents the poly Z of your qubit, right? So this is an A dagger A times Z coupling. And chi is just the strength of this coupling, and this is the dispersive interaction strength. So now what you do is you prepare your qubit in the state, you have some state in your cavity, and you prepare the qubit in the state G plus E over square root of 2, right, or the plus state. So now you apply a unitary, so you evolve this state under this Hamiltonian, so you have e to the minus IHT. So this is the unitary that you evolve under. So this is I chi A dagger A. Actually, I'm going to change this slightly. So the Hamiltonian that I will put here is 1 minus Z minus 1 minus Z over 2. It's still the same. I've just added a shift of A dagger A. This is essentially, it'll just allow me to write the unitary out in a cleaner form. So this guy is basically chi A dagger A E with the minus sign. So now when I expand this guy, I expand this, it'll look like, again, do the math, you'll see that this unitary operation corresponds to, if the qubit is in GG, nothing happens to the cavity, and if qubit is in EE, then I do a E I chi T A dagger A to the cavity. Okay, let me be a little bit, so there's a tensor product here. Okay, so now what you do is you started with this state, right? This was the state of the cavity. So you applied this unitary. State of the cavity. So if the state psi is a +1 eigenstate of the parity operator, that is this operator. So I can choose, so I'll choose chi t equal to pi so that this actually becomes a parity operator. So if psi is the +1 eigenstate of the parity operator, this guy, this whole state just becomes G plus E tensor psi. If this was the -1 eigenstate of the parity operator, then let's change the color, then this would be G minus E tensor psi, right? So basically, you start with the qubit in a superposition state, and cavity is in some state. You evolve them under this unitary operation. If the state of the cavity was a +1 eigenstate of the parity operator, the qubit returns to the state it started with, which was G plus E. If it was a -1 eigenstate of the parity operator, the qubit will return to the G minus E state. So using this interaction, you know, at the end of the day, then you just measure your qubit, you know, with whatever strategy you have to measure the qubit. And then you basically, by measuring the qubit, you know what the state of your cavity was, in the sense that whether it was the +1 eigenstate of the parity or the -1 eigenstate of the parity operator. And so you can use this information to now, you know, go back and correct the state. Yeah.
And Shruti, just to make sure that everyone's on the same page, what exactly is the space for psi and the space for GE? So you're sort of referring one to qubit as one to cavity, but like how big are those Hilbert spaces?
So this when I say, yeah, this is a bit confusing. So when I'm explaining this, the qubit space is just a two-dimensional system. It's like your regular, you don't care about what other states that are available in your system. It's just a discrete two-level system. So it's state G, state E, and that is it. So in your transmons, you have your computational states of your transmon, which is G and E. In your trapped ion systems, you have whatever your hyperfine states or whatever states you're using to encode your qubit is what I'm talking about. So that, when I say qubit in this explanation here, it means a regular qubit, and then I'm going to refer to A as the cavity. Or I can also call this as ancilla qubit, because this is like an ancilla which you're using to determine these whether there was an error on the cavity qubit or not. Okay. So as I said, this strategy has been implemented, and people have performed error correction and shown that the error correction is actually successful. We are able to preserve the state in the cavity for a longer time. Now, let's look at what it was this bad error that I was trying to tell you about. So remember, the unitary that we are implementing goes like this, right? So the unitary at some time t is just the Hamiltonian IHT. Let me replace this guy with the capital T here. So I said that I evolved this system for time t such that chi t is equal to pi, and after that I measure the qubit I measure the ancilla qubit to determine if there was an error on the cavity qubit or not. But you see this is taking some time. I go from 0 to capital T time for this gate to implement. So at some time in between, so from 0 to t, at some time in between t, this is the unitary that is happening in the system, which is just G tensor I plus E to the I chi t a dagger a. Now suppose there is a bit flip on the ancilla. Suppose at this point in time, G goes to E and E goes to G. So there's a bit flip error on the ancilla qubit. Then if I apply bit flip error on the ancilla qubit, bit flip on ancilla after a time t, then this will just become E tensor I plus G tensor E to the I chi t a dagger a, right? I just flipped. And after this, the gate continues, right? After this, the same unitary happens for time capital T minus small t, right? So basically I have to apply U t minus t here. Now, So U of capital T minus T is just G tensor I plus E. Sorry about this. This is a little bit of math, but I think it's useful to see this work out. So now I want to determine what this guy over here is, given that this is my U capital T minus T. So this guy will then become, so I'll have G tensor e to the I chi t a dagger a plus e tensor e to the I chi capital T minus t a dagger a, right? So this is base, you thought you were implementing the unitary U of capital T, but what you've actually done is implemented this unitary now. Because of a bit flip in the ancilla, you did not end up implementing this unitary, but you actually ended up implementing this unitary. Okay, so now what happens? So now again, you know, remember chi t was pi. So now if I apply this guy to my state, input state, which was qubit in G plus E and the cavity in some state psi, then what I have at the end of the day, suppose psi is the +1 eigenstate of the parity operator, then the state that comes out is G e to the I chi a dagger a, sorry, there's a time here, t, psi plus e tensor e to the minus I chi t a dagger a psi. So now if you measure the qubit in G plus E, then the state of the cavity is not psi anymore. The state of the cavity is going to be cos chi t a dagger a applied to psi. And if you measure the qubit, yeah, I think you measure the qubit in G plus E, and this is going to be the state. So now you have a back action on your state in the cavity, because there was a T1 error in the ancilla, and this error is not correctable. This is a high weight error, and this is not correctable. This is not an A error or A dagger A error. This is like, you know, I mean, if I expand cos term, it'll be, you know, sum of, you know, it'll be 1 minus chi t A dagger A minus chi t squared by 2 plus chi t 4 or something like this, right? You basically can expand it, and you see that you get really high order terms here. So this is a high weight error that I was talking about, and this error is not correctable. This does not satisfy the error correction criteria, and you can check it. And so we have a problem. So basically, when you try to perform error correction, you introduce a new type of error, which is coming from the errors from the ancilla. It's not naturally present in the oscillator. This type of error is not naturally present in an oscillator. It's coming because you coupled your oscillator to some external thing, and the errors from that external thing are propagating back into your system and introducing an uncorrectable error. And this is what is limiting, this is what limits the current binomial, this is what limits the current error correcting, bosonic error correcting codes. The kind of codes that we will talk about today, there are some other codes that are still fine, but let's not go there. But most of the bosonic codes are affected by such backpropagation of errors from the ancilla onto the cavity. So basically now I need some other way, some other code on top, which can protect me from this error.
So Shruti, I think we have a clarification question, which is, are you measuring the cavity or the qubit, and what exactly, like, what's sort of the order here, and what kind of measurement is this in the real world?
So I'm indirectly measuring the cavity using a qubit, because what what I want to measure for error correction is this operator. This is the parity operator that I want to measure. But how do I measure this? How do I give you a cavity? How the hell are you going to measure this, right? The only way we can, well, not the only way, but the obvious way, or the way we know how to do it so far, is to indirectly measure this by coupling it with an ancilla, map the information about the parity onto the ancilla, and then read out the ancilla. So in this case, so this is similar, like you heard about surface codes from Austin Fowler and John Martinez, right? There you had to measure this 4-body XXX and ZZZ stabilizers in the surface code. So what you did was you put an ancilla qubit at the centers of your, between 4 data qubits, you put an ancilla qubit, then map the information about XXX and ZZZ onto the ancilla, and then you read out the ancilla that sort of indirectly tells you, whether there was an error on the data qubits or not. It's the same thing here. You cannot directly measure these stabilizers, so you indirectly measure them with an ancilla, and this is how you do it here. And in our case, the back action from the ancilla introduces an uncorrectable error. In the surface code, back action from the ancilla introduces a correctable error, in the sense if you have a big enough code, you'll be able to correct for it.
And just to be clear, following that point, there's a question that says bit flip errors on measure qubits are therefore high weight, and bit flip errors on logical qubits are low weight. I think there's a little confusion of what weight means in contrast to the surface code where all of these things are correctable, question mark?
So the errors that I'm correcting in the cavity are still low weight, right? Those are the things that I'm correcting for is M1, which is A, and M2, which is 1 minus P, A dagger, A. These are, for the code that I've built, these are still low weight errors, right? These guys, for example, this is only correcting Fox state 4 to Fox state 3 or Fox state 2 to Fox state 1. This guy doesn't change the Fox state at all. 4 remains 4, 0 remains 0, 1 remains 2 remains 2, right? So this is not, so these are not, these are still low weight errors, whereas this is a high weight error because this is actually going to introduce a phase flip error in my code. So let me tell you how. So suppose you have a superposition state of 0 bar, x0 bar plus y1 bar, where, okay, so your 0 bar is 0 plus 4 over square root of 2, and y is, Fox state 2. If I apply cos chi t, a dagger a, to this state over here, I will get, so I'll have x0 plus cos chi t4 over square root of 2, and I'll have here cos chi t2 times 2. So suppose chi t is pi over 2, then, oh, sorry, I forgot to put a 4 here. Yeah, so if chi t is pi, suppose the error in the qubit happened when t was pi over 2 chi. In that case, this guy then becomes x0 plus 4 pi square root of 2, but this guy picks up a minus sign over here, and you're lost. You have a phase flip error here. So you cannot correct this in this code. You have to make a bigger code, a different code. I have to concatenate it, but you cannot do it at this level here.
But could you use another ancilla to detect that high weight error and then correct it, or?
Absolutely. So there are many proposals to do this. So you could have a, I'm forgetting about the name now, but you could actually have a second ancilla there which detects a bit flip error on the first ancilla. And basically, if that happens, then you can throw away the result and start over. But if the back action has already happened, there's no depending on the exact scheme you use, you might just have to throw the result away and start over. You may not be able to reuse the state in the cavity. Because you see, it's important to know when this error happened and not just that it happened or it did not happen. So that's not always possible, but there are many ways to overcome this. You can, I'm forgetting this particular strategy, which is called flag, yeah, so there's something, you can use flag qubits, that's right, flag qubits to, overcome some of these problems here. But yeah, again, you need extra qubits to do this. There are qubits which are called bias noise qubits, which don't have bit flip errors. They have only phase flip errors. For example, a fluxonium is a bias noise qubit. The Kurkat qubit is a bias noise qubit. So you can use those kind of qubits to, which don't have this bad kind of error as an ancilla. That's also possible to do, but it has not been done yet. So there are strategies to overcome this, and people are trying to implement them.
And you mentioned that different codes could possibly correct for this. So what is the sort of cost of those different codes? Like, why don't we just use them then instead? Do they require more qubits or?
Yeah, so you can, as I said, I mean, naively, you could just encode your ancilla. You can encode an ancilla into, a bigger, you could encode an ancilla into a bit flip code or something like that to prevent those errors from back propagating. It just increases the size of the code. So it's not, again, the point is not that you cannot correct for it. The point is you want to correct for it in a hardware efficient manner. And that's hard to do. That's the challenge.
And sort of the corollary to that is then why is limiting the number of, like, what in practice keeps you from using more and more Fox states?
Oh yeah, so I mean, you can use more and more Fox states, but depending on your actual system, you never actually have a harmonic oscillator. You have, what you get is an harmonic oscillator in real life. And so if those anharmonic terms can introduce new forms of errors which your code will not be able to correct. So there's a lot of things that you have to think about when you start building a real error correcting code like this. Yeah. So for example, the codes that I'm going to talk about, like the binomial code that I'm going to talk about today, or GKP code that I'm going to talk about today, none of them can actually sustain back action from the ancilla. As I said, I don't think, yeah, so okay, here's my claim. No bosonic code that I've seen so far can sustain back action from the ancilla. There's some, so the codes that I was thinking about earlier was these stabilized cat codes, which actually don't need an ancilla like this to do error correction at all. So that's a completely different beast, which I don't want to go into today. But vast majority of the bosonic codes, you will suffer from this back action of the ancilla. There are some ways to go around it, and that's the things that I work on and I'm very excited about, but that's not what I want to focus on today.
One last question. In this code, why do you encode the logical state to be a superposition of 0 and 4 rather than it just being 0 or just 4?
So if you just do 0 or just 4, it will not satisfy the error correcting criteria. Simple as that. So basically the idea, that's another thing that I wanted to go explain to you, which I think is the last thing that I'll explain before we take like a 10-minute break, is that to satisfy these error correcting criteria, there's some intuitive things that you need to have. So for example, I wanted to show you that if you want to error correct against a single photon loss channel, you basically have to have two code words which have the same average photon number, and that their support on the Fox space is separated by more than 1. So I'm going to explain what this is in just a minute, if you can move on. And this brings me into binomial codes. This is the smallest binomial code, and I want to explain to you what are the necessary conditions that we need to meet for making such a code, and then that will help us build the binomial code in a sense. So one of the things you can immediately see, so remember our error correction criteria. Our error correction criteria that you needed to satisfy was 0 m I dagger mj, 0 was same as 1 mi dagger mj, 1 and then 0 mi dagger mj. Oh, mi dagger mj. This had to be 0, right? These are the two things that I needed to satisfy. Let's so let's look at this first. So this is criteria 1, this is criteria 2. Let's look at the first criteria, and let's look at it for a simple case when I is equal to j. Okay, so basically mi mj, oh sorry, mi dagger mi, 0 has to be equal to 1 mi dagger mi 1. So m1 is square root of BA, so m1 dagger m1 is BA dagger A, m2 is square root of 1 minus BA dagger A, m2 dagger m2 is 1 minus BA dagger A. So that this condition basically means that you want 0 A dagger A 0 to be the same as 1 A dagger A 1, and you want 0 1 minus P A dagger A 0 to be the same as 1 minus P A dagger A 1. These two conditions imply that the two logical states that you choose must have the same average photon number. That's it. If they have the same average photon number, this condition is going to be satisfied. And so at least one thing you have checked off. Yes, that error correction criteria will be satisfied. So if you just use the encoding of 0 and 2 rather than 0 plus 4 and 2, then this condition will not be satisfied. They won't have those two states and are going to have the same average photon number, and this state condition will not be satisfied. The other condition that you need to satisfy, okay, let's look at the other conditions, right? So now I want to also, so when I and j are not the same, so in this case, something like this, m1 dagger m2 0 has to be the same as m1 dagger m2 1, and then of course the orthogonality condition. I still need to satisfy these two. So in order to understand when these two conditions can be satisfied, let's expand the logical 0 and logical 1 states in the photon number basis. I can always do that, right? So I can always write 0 as some superposition of Fock states and 1 as some superposition of Fock states. Right, so if you look at, you could, for example, you can look at what is the support of these logical states on the Fock basis. So Fock state 0, 1, 2, 3, etc. So clearly, if the Fock state 0 and Fock state 1 have support on if the logical state 0 and logical state 1 have orthogonal support on the Fock basis, those two states are going to be orthogonal, right? So for example, in the code words we looked at for 0 plus 4 by square root of 2, the support was on the Fock state 0 and Fock state 4. This was support of the 0 bar state, and the support of the 1 bar state was on the state 2 here. And clearly these two states are going to be orthogonal. So if the two code words have different supports on the Fock basis, they're going to be orthogonal. So that's one thing that we have satisfied. Now, of course, we have to satisfy these error correction criteria. And you can check, it's a little bit of a math to check, but you can check that if 0 and 1 states have supports which are separated by 1 Fock state plus or minus 1 Fock state, then these two error correction criteria will be satisfied. That means that if the logical state 0 has support over, has a non-zero support over a Fock state n, then 1 bar cannot have a support on Fock state n plus minus 1. If these two conditions are satisfied, then all my, so if this condition plus the fact that you have the same average photon number in the two states are satisfied, then your error correction criteria is going to be satisfied. And the smallest code to do this is the code that I wrote before, 0 plus 4 and 2 encoding. And now I can do similar analysis. I can extend this even further. Suppose I have 2 photon losses. So I have I have one single photon and two photon loss. So I have M1.
Shruti, before you go on, there are a couple questions I think will help for clarity, which is a couple are related to average photon number. And first, can you just define it exactly? And second is sort of, so basically, do we choose two physical states with the same average photon number as logical states? And then single photon loss can be detected without measuring the logical state. So I think those sort of two things. First, define it and.
Right. So the average photon number, again, so if you were able to go through the pre-lecture notes, the average photon number is for any state is expectation value of A dagger A, which is psi, A dagger A psi. So basically, if I want to choose two logical states, I want to have 0 bar A dagger A 0 bar to be the same as 1 bar A dagger A 1 bar. So this means that the average photon numbers in the two logical code words are the same. What was the other question about whether, so you need to satisfy this condition as well as the fact that the support of the two logical states in the Fogg basis is separated by 1, plus or minus 1. So if for example, Fogg state 0 has support on logical state 0 has support on Fogg state 3, then logical 1 cannot have a support on Fogg state 2 and Fogg state 2 and Fogg state 4.
Then the graph that you showed then is the support of those.
Yeah, that's right. So
on
the
those.
Right. So the graph I showed here was basically the support. So whether I have 0 photons or 1 photons or 2 photons or 3 photons or 4 photons here.
So
maybe I can draw
like the modulus squared, for instance, of the coefficient in front of each of the.
Sure. Yeah, you can draw the modulus square. So basically I'm looking at photon number distribution of the state, right? So I have 0 photon, 1 photon, 2 photon, 3 photon, 4 photon, 5 photon, and so on. So for the logical 0 state that I chose, I had support of P0 was non-zero and P4 was non-zero. Everything else was 0. For the logical 1 state, I had P2 was non-zero, right? So there's, you see, you got a plus minus 1 difference in the Fogg states. So basically, your zero state has support on 0 and 4 photon Fogg state. So the logical 1 state cannot have support on 1 and 3 photon Fogg state, which it did not. The logical 1 had a support on the 2 photon Fogg state. If logical 1 has a support on 2 photon Fogg state, then logical 0 cannot have a support on 1 and 3 photon Fogg state, which it doesn't. It has support on 0 and 4. So basically, the idea is that the number of errors that the number of photon loss events you want to correct, that's how disjoint the Fogg state support needs to be. And I'm going to explain that just in one more second. But there was a question about some measurement, like what am I measuring or something? But this whatever I've said has nothing to do with measurements. This is just saying what properties should the 0 and 1 logical states satisfy so that the error correction criteria will be satisfied. It doesn't yet tell you what you need to measure, how you need to measure it to satisfy the error correction criteria. That's not included in this so far.
What about measuring says a single photon loss can be detected without measuring the logical state, right?
Sorry, single photon loss can be detected without measuring the logical state?
Yeah.
How?
I think that the question was, so basically we choose two physical states with the same average photon number as logical states, and then a single photon loss can be detected without measuring the logical state, right?
No. I mean, so you're measuring single photon. Sorry, I think I got confused. Yes. So you're measuring whether the error happened or not, whether the single photon error happened or not by measuring not the logical state, but you're measuring the stabilizer for the state, which was the parity operator. So, but this is, Okay. But that has nothing to do with conditions for error correction.
Thanks. Another question is, can you intuitively explain the second criteria?
Intuitively explain the second criteria. Yeah, I can explain it the second criteria. So basically you want orthogonality condition, right? So if suppose one of your logical states was 2, but if you have a single photon loss, then single photon loss can bring 2 to 1, right? I can bring 2 to 1. That's what single photon loss does. So basically, naively, for the orthogonality condition to be satisfied, you don't want to have your 0 state to have any overlap with the 1 state for the error correction criteria to be satisfied. That's it. And similarly, if there was a single photon loss on this Fock state 4, then it would bring you down to Fock state 3. And the easiest way for the error correction criteria to be satisfied is you don't have any support on that state for the logical 1 state. That's it. So basically, yeah, you just need to make sure that photon loss events don't naturally cause any overlaps between otherwise orthogonal states.
And Shruti, to follow up on that, there's a question that sort of relates back to cubic codes and saying, is the reason for the difference being larger than plus or minus 1 in Fock space? Is this like saying you don't want to use just like 0, 0 and 1, 1, like a 2 qubit type of repetition code as the logical state instead of using 0, 0, 0 and 1, 1, 1, because the distance between the logical states has to be large enough to detect an error?
Exactly. Yeah, exactly. That's what it is. The distance between the 2 states has to be large enough to detect errors. That's right. So in general, again, you can generalize this. Suppose you have 2 photon loss events. So you can have single photon loss event. You can also have a 2 photon loss event. And again, to complete the condition for cross operation, you need to have 1 minus p, a dagger a minus q, a dagger square everything under the square root. And if you have such a loss channel, then you need to, again, the error correction criteria will be satisfied if the 2 logical states, 0 and 1 that you choose, have the same average photon number. And the support of 0 and 1 on the Fogg basis support is greater than plus or minus 2, basically. So if 0 has a support on Fock state n, then 1 cannot have a support on n or n plus minus 2, basically. That's it. Again, you can generalize it. For n photon loss events, again, for the error correction criteria to be satisfied, the 2 logical states should have the same average photon number, and the Fock state support should be greater than, plus minus n, basically. The difference should be greater than plus minus n. And so this is what a binomial code is. It is generalized for any photon loss events. And I can just write the code words for you. So the code words for a binomial code, which can correct for up to S photon loss events. That's the terminology I've used. So if you want to correct for up to S photon loss events, then the code words are 0 bar is 1 over square root to S. P is an integer, it's even going from 0 to S plus 1. You have this binomial coefficient, which actually ensures the average photon number is same. P multiplied by S plus 1, and 1 is just square root of 2 to the S. P is odd, going from 1 to S plus 1, square root of S plus 1 CP, P times S plus 1. This is the binomial code. It can correct for up to S loss events. You can also generalize this to correct for, S1 loss events, S2 photon gain events, and S3 A dagger A type events, which is related to frequency fluctuations. Yeah, I don't know what to call them. In oscillation, in harmonic oscillator language, we call this pure dephasing events, but I don't want you to get confused with dephasing in a qubit, so I prefer not to use this term, but think about this as just coming from frequency fluctuations in an oscillator. You can generalize a binomial code to correct for any number of loss, gain, or pure dephasing events. Again, the problem with these codes is that no matter what you do, you're going to have a high weight event like e to the I pi A dagger, e to the I theta A dagger A, which will come in when you use a ancilla qubit to try and measure if an error happened or not and try to correct for it. So that's, you'll have this problem. Unless you use extra flag qubits, encode your ancillas in some other error correcting code, or use bias noise ancillas.
Shruti, quickly, do you mind changing your color from blue for a particular audience member?
Sorry, yes. Do you want me to rewrite anything? I'll use black.
Black's good, thank you.
Okay.
I think your last remark sort of answers the next question. Does the idea of a single photon loss correspond to having a single qubit error in a conventional QEC system?
A single photon loss correspond to having a single qubit error. It's hard to say. Yeah, I think there is a way you can think about it like that. It's more like amplitude damping event, but yeah. So you can think about a single photon loss as having a single error. I think that's okay to think about it like that. But it's a single photon loss. So if you have a 5 qubit code, then that single photon loss could happen anywhere. When I talk about 2 photon loss, it's like having 2 correlated errors on your qubits. It's more like that. 3 photon loss is having 3 correlated errors on your qubits. It's more like that. Or having 2 errors at the same time on your qubits in some sense.
Why do the 2 logical qubits have to have the same average photon number?
I just did that. That's to satisfy the error correction criteria.
If you use 048 instead of 024, will that be able to tolerate more photon loss?
If you use 048, if your aim is to correct for a single qubit error, then there's no point in using 8 because 0 plus 4 is enough. You could use it if you wanted to. Actually, no. You have to make sure that again, you have to make sure that the average, the 2 logical states that you use have the same average photon number. So if you're using a superposition of 0 plus 4 plus 8, the other state cannot be 2 because this state and this state have different average photon numbers. You need to change the coefficients here in the right way so that they have the same average photon number. Otherwise, it'll cause an uncorrectable error.
One final question on photon loss. After detecting a single photon loss, how do we correct it? Do we just add another single photon to the cavity?
Good question. So as I said, it depends what you want to do. So in the smallest binomial code, the one we looked at, you just apply unitaries to correct it. So for example, you started with the 0 plus 4 state, and say you went to the 3 state, and if you started with 2 state, you went to the 1 state, and you know that this error has happened. So you can just apply a unitary operation to actually, bring these states back. And this is what they do in the experiment. I can't remember the exact form of the unitary or how they're actually implemented, but you can apply unitary operation to bring everything back. Even when you so you can have a single photon loss, or you could, M1, this corresponds to M1 of A. You could also have M2, right, which is 1 minus BA dagger A. And in that case, again, you have a unitary operation which can recover you, bring you back onto your state. It's just that the unitary looks a bit more complicated. In terms of qubits, if you detect an X error, you can just apply another X if you wanted to, another poly if you wanted to correct for the error. In certain bosonic codes, you actually don't have to correct for errors. You just need to track for errors. In the case of this particular, in this small binomial code, you have to actually correct for errors. And the reason is that if you don't correct for errors, these two states don't satisfy the error correction criteria anymore. So if there's another single photon loss event after this, then you won't be able to recover from that. Therefore, you actually need to correct for the errors before the next single photon loss happens. You actually have to come back to this space.
What do you mean by bring everything back?
Bring everything back in the sense that an error has happened and you have gone to a different qubit space or a different space on the oscillator. You're not in your code space anymore. Now, bringing it back is just apply a unitary to bring yourself back into your code space.
Great, thanks.
Okay, so let's have like a 5-10 minute break and then we can come back.
Do you want to answer the final 3 questions before that, or should we postpone it too?
And let's take more questions.
Okay. So is there an intuitive understanding of the operator M2? M1 is 1 photon loss operator, say.
Yeah. M2 is basically in quantum optics language, we call this a photon jump event, and this is no jump event. This is actually you lose a photon. But the point is that even if you lose a photon, then the environment knows that there was very likely that you had no photons in the cavity. So the environment sort of projects you onto a new state which has a lower photon number in it. So this is that no jump event, basically. Yeah. So I mean, if you know master equations, the actual mass, the most common channel is like, in terms of master equation, you describe the evolution of your density operator rho dot as minus h rho with some Lindbladian evolution, and the Lindbladian is actually kappa a rho a dagger plus minus a dagger a rho over 2 minus rho a dagger a over 2. M1 corresponds to this guy, M2 comes from this guy. This is just like energy relaxation that's happening. So if you decompose this Lindbladian into in terms of channels and in terms of cross operators, then to the lowest order, these are the 2 cross operators that you would get. Also, cross operators are not, let's say, unique. So I have chosen to write it in this form, but some other people might choose to write it in a different form. It doesn't matter. Different cross operators can represent the same channel, basically.
Shruti, so maybe the cross operators, maybe it's understandable how the environment can sort of suck a photon, but there's a question asking, how can a unitary operator add energy, i.e. the last photon back to the system? Seems a little...
How does a unitary I mean, don't think about it as adding or subtracting energy or anything like that. It's just, I'm basically doing a unitary in the restricted Hilbert space of, these guys. I don't understand what is the issue with that. I mean, like, for example, you have a transmon. You accidentally go from you put the transmon in an excited state, it goes to the ground state. You just apply, a drive to your transmon and you put in, you flip your transmon from the ground state to the excited state. Similarly here with drives or with from another qubit, you can get the energy to implement the unitary, which flips you, which takes you from the state 3 to this state and state 1 to this state. I mean, in some sense, you are applying drive somewhere. You have to give it energy. So you create you create a Hamiltonian, you create a unitary with drives or something like that to actually add the photon back in, to add the energy back in. Sorry, go ahead, Nick.
No, just there's another question that will take you in a different direction. So I would like, yeah, if you're finished with this. Okay, so the other question is sort of to take you back to your example of using the 8 photon Fock state. You mentioned that that example would share support on Fock state 2 and prevent you from satisfying our criteria. But I think the root of the question is more in the next sentence, which is how do we know whether something shares support on Fock state 2?
But this doesn't have any support on Fock state 2. The reason this doesn't satisfy the error correction criteria is because the average photon number in this state is going to be different than the average photon number in this state. That's why it doesn't satisfy the error correction criteria. Whether you want to see if a state has a support on certain Fock state or not, you just look at, say I give you a state, and if you want to look at whether it has a support on Fock state n, you just calculate n psi, right? So if this is 0, then it doesn't have any support on that state. If it's not 0, then it has support on that state. I'm not sure if you were asking this or in experiments, how you know whether something has a support on some state or not. I'm not sure.
The next question that popped up in response to that was how about 0 plus 8 compared to 4? Is that like, yeah, there's no more to the question than that, but is
absolutely,
that
yeah, use 0 plus 8 and 4. Absolutely, use it. Use 0 plus 8 plus 0 plus 8 and 4 if you want to. Go ahead. It's just it just has a higher photon number rate, so if you're not worried about using more Fock states in your experiments for some reason, then go ahead and use it.
Right. So there might be some trade-off practically between the error rates that might occur, but you should evaluate whether you should or shouldn't do that.
Yeah. Okay. I mean, so the point, so 0 plus 8 is not actually buying you anything compared to just using 0 plus 4. So yeah.
And I think people are really confused what the definition of support is exactly. Is it really the same thing as overlap?
Yeah, absolutely. Yeah. Same thing as overlap.
And okay, I guess one more. They keep coming in as we go, so I think that's good. So, what does the average photon number represent? Sort of physically, is it? Yeah, like physically, what would I see with a different average photon number? Could I measure that?
Yeah, I mean, you can measure expectation value of photon number operator in a state if you wanted to, and they'll be different for 2 different states, or they'll be the same for 2 different states.
I guess the extension is the environment could measure that, and so if they were different.
Yeah. I mean, basically, so the reason we need the average photon number to be the same is to satisfy one of the no distortion criteria, which is needed to make sure that basically the no distortion criteria says that the different code space, the code words remain indistinguishable in different spaces. And so if they don't have the average photon number to be the same, then the environment can distinguish and you've lost the information. Another way to think about it is that the no distortion criteria also comes from the fact that you don't want to just error correct the state zeros and ones, you want to correct errors, superpositions of state zeros and ones. So for example, you want to correct the plus state. So if the no distortion criteria is not satisfied, then you won't be able to correct for this to protect the superposition state, for example.
Sorry, Shruti.
Yeah.
To follow up on that a little bit, for that reason, 0 plus 8 and 4 won't work, right?
Oh, they don't have the same photon number, average photon number?
No, they do, but well, okay, not for that argument, but the quantum information will be distorted because the photon number annihilation operator acting on both states will, in general, corrupt a superposition. Because A on 8 pulls out a square root of 8.
No, that doesn't matter. If the average photon number is satisfied, it's the...
Sorry, maybe I jumped the gun there.
So there's also square root of 2 here. So 0 plus 8 by square root of 2, if I apply... yeah, but I mean...
Sorry.
I think this will satisfy all the error correction criteria.
Sorry, yep, I jumped the gun, sorry.
Just to jump in, I think there's a name for this as well. I think this is called the noon state or the noon code. And it's sort of a generalization of the binomial code.
Oh, you're saying the noon code is a generalization of the binomial code, or binomial code is a generalization of the noon code?
Sorry, the second.
Okay, yeah.
Yeah.
Sorry, so getting back to our question list here from the audience, there's a question about transmon qubits. And it says that in transmon qubits, we use a level of anharmonicity to distinguish different Fock states. Is that the same here? Because it seems a little more complicated, or is this an irrelevant question? And I don't think it's irrelevant, so I asked it.
So in a transmon, we use the anharmonicity to selectively couple between two states. In a harmonic oscillator, we cannot do that because there's no anharmonicity. If I add one photon, 2 will go to 3, 4 will go to 5 or whatever. So there's no, it's very, so this is the problem. So if I want to do anything to a harmonic oscillator, I need an anharmonicity somewhere. The moment you add anharmonicity, your air channel is not the air channel of a oscillator anymore. It's completely different beast, and these codes are not necessarily designed for that. There are codes which work under anharmonicity, and the KERCAT is an example of that. That it uses anharmonicity to its benefit to implement a bosonic code, but the one I'm talking about right now doesn't. It should not have anharmonicity. Let's say. But maybe did I answer the question?
I mean, maybe the statement is it's harder to do in a harmonic oscillator, and that's why we need other ancillas and different couplings. Right.
Yeah. So we need transmons, like in superconducting circuits, we need transmons to do anything to make a bosonic code work. Otherwise, we can't do it. And yeah, so this is why, when I was talking about measuring the parity operator, I actually had a qubit out there to, I had a regular qubit to do this. There's the GKP code, which basically doesn't need any anharmonicity, except for the state preparation. Even for error correction, it doesn't need any anharmonicity. So that's a nice feature of the GKP code, but we will get there when we get there. And I said technically it doesn't need harmonicity, but it does eventually need it. There's a lot of complications going on, but in principle, it doesn't need it except for state preparation, but in practice, it does.
Next question, and unless you want to continue, yeah. So the next question is how do you add or remove photons from the cavity? Do you just have an extra drive line? Like, I think there's a question of physicality sort of coming in. So
again, I never add or remove a single photon. I apply unitaries to my cavity, and the way I apply unitaries to my cavity is by applying drives either directly to a cavity or to a qubit, for example. Yeah, I mean, I can, so it's a bit, so so for error recovery, for the binomial code, the unitary looks a bit complicated. So I don't, I mean, basically what I do is what I want to do is get a unitary, which basically, you know, couples my state 3 to state 0 plus 4 over square root of 2, something like this, Hermitian conjugate plus 1 going to 2, something like that. You know, basically, I just need to create some unitary which does the operation that I want to. Now, even to create that unitary, I do need an ancilla again. So in the binomial code, I do need a regular qubit ancilla, a transmon ancilla, to implement the unitaries that I need to recover my states. This is not always true for the GKP code, for example. Firstly, in GKP code, you can always keep track of errors. You don't actually have to go and apply a correction operator. Even if you did want to apply a correction operator, in the GKP code, all you do is apply a single microwave drive, which the Hamiltonian for which looks like this. So you just apply a drive, which effectively creates this Hamiltonian, and you evolve the GKP state under this Hamiltonian for a certain amount of time to recover your state. That's it. So you're not actually adding one photon at a time or anything like that. You're creating unitary operators. Okay, so I'm going to pause for a second. Let's take just 5 minutes. If you guys want to drink water, I'm going to drink some water. And I'm going to open up a new set of notes. And I think, yeah, I have time. So maybe I can do cat codes as well. I think that, yeah, let's stick to the schedule. Okay.
I don't know what the break time is, but you have a question which sort of sets the stage, I think.
Yeah, go ahead, please.
Like.
Yeah.
Which is, since we have an infinite dimensional Hilbert space, what prevents us from creating, say, two logical qubits from a single photon, or sort of why can't we just use a single photon? Is it because we wouldn't be able to do single qubit gates? Or
why can't I use single photons? What do you mean by why can't I use single? So so in the beginning, we talked about using Fock state 1, which is a single photon Fock state, and Fock state 0, which is a 0 photon Fock state, to encode my qubit and do error correction that way. But we saw that this was not hardware efficient, in the sense that even if I have single photon loss, the error correction criteria cannot be satisfied. So the only way, if I use this encoding, then I need 5 cavities, 5 harmonic oscillators with this encoding to be protected against a single photon loss error. Was that? Yeah, okay, great. So now I think that, because there's so many discussions, which I love it, but I'm going to skip over, I was going to do the cat codes, but I think I want to do GKP more, because I think you folks will like that more. So I'm going to skip over cat codes and I'm going to do GKP. But the reason I picked up binomial cat code and GKP is because all these 3 have been demonstrated experimentally in the lab. We have seen, increase in lifetimes. So Alec, who was one of the panelists here, and he will also join you later for the Gather Town social discussion. He was also one of the people who has done error correction on the GKP surface code, for example. So that's the reason I picked them. Because of interest of time, I'm going to skip over the cat code. That was actually the first Bosonic code in which they demonstrated error correction. But unfortunately, I'm going to skip it over and I'm going to go to the GKP code. It's a little bit harder to understand, but I think it's worth it. Also, with the GKP codes, there's a lot of pi's and 2 pi's in the expression that is a bit hard to keep track of. So I'm going to go back to my notes to make sure I'm writing the right things. So please bear with me on that. So I have to go bring my mouse back here. Okay, So we looked at binomial codes. Let's look at the GKP code, which was invented by Gottesman, Kitaev, and Preskill back in 2001. And this is actually the 20th anniversary of the GKP code. And it when it came out, it was like certainly well ahead of its time, right? Like the code was just so complicated, you could never imagine building it. But now they have been demonstrated in 2 experiments. The first one was by Jonathan Holm in trapped ions. Then the next one was in superconducting circuits in Michel Zavary's lab. And, Alec was one of the leads in that experiment. So let's look at what these codes are. Right, so for the GKP code, I need to use the displacement operator in a cavity. Now, in the pre-reading notes, I had written down what a displacement operator is. So hopefully you're not shocked to see this, but no, well, if you are, then you are. So the displacement operator is written as D of alpha, and it's defined as e to the alpha a dagger minus alpha star a. So this is we read this as displacement by alpha, and then alpha is a real number. Alpha is a complex number. So it's a C number, and A and A daggers are, A and A dagger is just your photon annihilation and creation operator. You can have displacement by some other C number beta, which will just be e to the beta A dagger minus beta star A. Okay, and now in the homework, if somebody had the patience to actually work out some of the problems, then you would have seen that there's a property that if you have a displacement alpha times displacement beta, then this is actually equal to e to the I alpha beta star minus alpha star beta over 2 displacement of alpha plus beta. And similarly, then displacement of beta, displacement of alpha is going to be e to the I alpha star beta minus alpha beta star over 2 d of alpha plus beta. So now, basically what you have is that the displacements don't commute, or they commute up to a phase. So basically you have d alpha d beta is equal to e to the I alpha beta star minus alpha star beta d beta d alpha. Okay, so now you see that if I choose alpha beta star minus alpha star beta to be equal to plus or minus 2 pi I, then plus or minus 2 pi, then this is going to commute. Did I mess up the i's here? Maybe this is not there. Can one of the panelists confirm the formula? Are there i's there or not? Anyway, so basically if you choose alphas and betas such that alpha beta star minus alpha star beta is plus or minus 2 pi I, these displacement operators are going to commute. And if you choose it such that this is equal to plus or minus pi I, they're going to anti-commute. Okay. So now what we do is I want to encode a qubit in the system, in my cavity, but it's a very weird kind of encoding. I'm actually going to, instead of writing the code word, I'm actually going to define the Pauli operators for the encoding. And I'm going to start from there and then tell you what the code words are. Okay, so notice that I can define an operator X, which is going to be my Pauli X operator, as D of alpha, and I'm going to define an operator Z, which is going to be Pauli Z operator, which is D of beta, and I'm going to choose alpha and beta such that this condition is satisfied. Alpha star beta is equal to pi I. then X and Z anti-commute, right? Then you'll have XZ equal to minus ZX. So this already you're seeing is that this is acting like the poly X and poly Z operators for your regular qubit, and your poly Y operator is just the product of X and Z, right? So basically you have defined the poly X, poly Y, and poly Z operators in which which will define your qubit space. Now you see that the other requirement for me to be able to call these poly operators is that the poly operator is square to identity, right? Now that means that my code space, in my code space, the action of poly X square, the action of poly Y, sorry, in my code space, the action of X square, Z square, and Y square has to be like identity for me to be able to call these as poly operators. So what we do is we use the code space, which is the +1 eigenspace of the operator called SX, which is the X stabilizer, which is simply X squared, which is D of 2 alpha. So we just use a code, we just use states, which is the +1 eigenstate of the X square operator and also the +1 eigenstate of the Z square operator, do beta. So now I have actually been able to define my qubit with the poly operators. My qubits are the +1 eigenspace. So the 0 bar and 1 bar states are +1 eigenstates of these two operators. So 0 bar SX is 0 bar, and 1 bar is Z, and also SX 1 bar is 1 bar, and similarly SZ 0 bar is 0 bar, and SC 1 bar is 1 bar. This ensures that my poly algebra is all satisfied. So these are now going to be the stabilizers of my code, or SX and SZ are going to be the stabilizers of the code. And these are going to be my poly operators. Okay. Up till so far, it's pretty mathematical. You will have a sense of what these code words are. I'm going to write the explicit definition in just a second.
And you have a question, Shruti, about the Y operator. Does this SX and SZ guarantee that Y squared is also 1?
Yes. Yes, because so the reason I did not write Y here, because I always confuse between the I, so I can't remember if Y is IZX or minus IZX. So
IZX.
Sorry?
It's IZX.
Okay, so if it's IZX, then Y square is minus ZXZX. This will be ZZXX, so Z square X square. So if the states are +1 eigenstates of X square and Z square, they'll also be the +1 eigenstates of Y square. Good. Okay, so this is the definition of the GKP code. That's it. All you need to know to work with your codes. You never actually need to know what your code words are. You just need to know what what your poly operators are and what your stabilizers are, and you have the code. But we will explicitly define or write down what the code words are. The original GKP code was defined using alpha equal to square root of pi by 2 and beta equal to I square root of pi over 2, such that you can clearly see that alpha times beta, this condition is actually satisfied with this definition of alpha and beta. Okay. So in this case, so this was the original definition. In this case, you can write the code words as superpositions of periodically displaced eigenstates of position and momentum operators. A lot to swallow, just bear with me, I'm going to write what these are. So now the position and momentum operators are defined like this. The position Q is defined like a dagger plus a pi squared of 2, and the position P is defined as I a dagger minus a pi squared of 2, position and momentum. Now, let's denote the eigenstates of P and Q as, just P and Q, and these are, the eigenvalues are basically continuous, right? The eigenvalues of P can be any real number, eigenvalue of Q can be any real number. So the eigenstate of, the code word 0 is actually written as a superposition of the eigenstates of Q, which are periodic. So like this, S equal to minus infinity to plus infinity. You take the eigenstates of the position operator with the eigenvalues such that the difference between, the spacing between the eigenvalues is 2 square root of pi, and just sum that up, and that is the logical zero state. Another way to write this is, so this sometimes is written as displaced displaced vacuum squeezed state. So the eigenvalues of Q and P are called squeezed states. So this is actually an infinitely squeezed state centered around 0. It's centered around the vacuum. It's vacuum squeezed state, and you basically just displace this state periodically, and you get the logical 0 state. And the logical 1 state is just the orthogonal sort of a state that has an orthogonal support, which is Q is to S plus 1 pi. This is equal to So in order to see what these states are, I can actually, like when we were looking at binomial codes, we were looking at their support on the Fox state basis. Here we're going to look at their support in the eigenbases of Q. Okay, so if I have on the x-axis, I'm putting the eigenvalues. So Q can be, somewhere between minus infinity to plus infinity, and I'm going to plot the overlap of the state 0 with the eigenstates of Q. So you see that it'll have a support on Q equal to 0, and we'll have a support on Q equal to 2 pi, 2 square root of pi. It will have a support on Q equal to minus 2 square root of pi, 4 square root of pi, and so on. Similarly, minus 4 square root of pi, and so on. So basically you have a comb of these squeeze states, superposition of this comb of squeeze states that form the logical 0 state. And the logical 1 state is going to have the orthogonal support. So it's going to be this guy here, which is Q equal to square root of pi, this guy here, and so on.
And Shruti, you're mentioning sort of eigenstates of Q and squeeze states, but could you clarify quickly what the difference is between a Fox state and an eigenstate of Q exactly? Since
yes.
We've been working with Fox states so far.
Yes, so Fox states are eigenstates of A dagger A, the photon number operator, right? So A dagger A times a Fox state N is just N times N. Squeeze states are well, the eigenstates of the quadrature operators are not the eigenstates of photon number state. In fact, there are superposition of many photon number states. Like you could write any state as a superposition of Fox state basis. You can do that here too, but it'll just be very complicated. The easiest way to do it is write it in the basis of the eigenstates of the quadrature operators. So in terms of the quadrature operators, so Q acting on Q is just Q times Q. I'm sorry, I could not figure out a better notation, so bear with me. And similarly, P times P is P, and you see the Fox states. The eigenstates of A dagger A, have this condition that they are integers, and they go from 0, 1, 2, 3, 4, etc. Right? Q and P can be anything. It could be goes from minus infinity to plus infinity. They're not bounded in the way that the eigenstates of A dagger A are bounded. From below, at least, of course, not from above. They're not bounded anywhere, and they can be continuous. So you can have Q equal to 0.000156, something like that. This is also related to, so for example, when you do homodyne measurements, this is what you're trying to measure. You're measuring Q, for example, when you try to do a homodyne measurement. When you do a photo detecting measurement, for example, you try to measure photon number state, whether you had a photon or not. So and this is also Qs and Ps are also then related to the amplitude and phase of the electromagnetic field, say you have in your cavity. A dagger is related to the, Q and P are directly related to the amplitude of the amplitude and phase of the electromagnetic field. A dagger is not really just the amplitude or phase, it's just the number state, basically.
Right, and so I guess the corollary, the next question on top of that is then, is the Q state like a thing that I can have commonly in my resonator?
Fantastic question. I'm going to come to that. That was going to be the next point. So yes, so Q, the eigenvalues of Q, actually, if you look at the, they have infinite photon numbers. If you try to calculate, Q, A dagger, A, Q, the average photon number is really large. So you have to physically, you cannot have that in a cavity. A lot of other things are going to go wrong before you can have a really a eigenstate of Q and P. What you do have is what we call, so the eigenstates of Q and P are also called as infinitely squeezed state, because if I measure QL, and I measure Q, and if I measure, it's the uncertainty in the measurement of Q will be 0, basically, if I prepare a eigenstate of Q. So these are also called as infinitely squeezed states. Of course, we don't have that in the lab. What we have is finitely squeezed states. And also because of the infinite photon numbers, you cannot normalize these states. These states are not normalizable. So what we actually do is actually have approximate code words, which if I now plot the support of the approximate code words, it looks like, so it's called a 0. So basically it's a Gaussian envelope over this guy. So you basically just put a Gaussian envelope like that. And this is, so this, for example, will be Q equal to 0, Q equal to 2 squared of pi, and so on. Similarly here. And then the red guy, the logical state 1 is going to be, okay, I'm going to be bad at drawing this. Something like that. These are normalizable. What we're essentially doing is taking these code words. So the approximate 0 state now is e to the minus delta square A dagger A applied to the exact 0 state. And then this becomes normalizable. And similarly, maybe I should call this approx. So approximate 1 state is now, you basically just apply a Gaussian. Basically, you add a penalty to adding more photon numbers, right? This guy is basically 0 for large photon numbers and 1 for small photon numbers. So you're basically adding penalty to having more photon numbers in your state. And that's all you're doing here. This is also like having this, it's equivalent to saying that you have a Gaussian envelope here. So in the lab, what we have are these states and not these states.
There's a question. We've chosen beta to be imaginary, so shouldn't the logical one be the sum of eigenstates of momentum?
We have chosen beta to be imaginary, so no. So the plus state is the eigenstate of momentum, not the, so 0. So the definition of 0 and 1 states are that there have to be eigenstates of the Z operator. which is d of beta. Wait, did I mess up beta? And so, okay, this is a definition. Okay, so beta is imaginary. This is I square root of pi over 2 a dagger plus a, right? So this is e to the I square root of pi over 2 square root of 2 times q. So this is e to the I square root of 2 pi q. No, this is fine. I think I made the right definition. So that now if you apply this guy to the 0 state, you'll get 0. And if you apply that to the 1 state, you'll get -1. Now, if, so, yeah, go ahead.
No, that looks good. I didn't want to derail you, but there are a couple questions on the envelope if you'd like to take them.
Yes.
So there's a question essentially, first, is this envelope a probability distribution? And second is, beyond that envelope, can you also make each of the lines wider instead of being an infinite impulse?
So each of the line is wider.
As a result of having this envelope.
Yeah, as a result, yeah, exactly. So as a result of doing this guy here, each of the line does get wider. And so these dotted lines was just as a guide for me to put 0 and 2 pi's and stuff like that. But so these, it's a Gaussian, each line becomes like a Gaussian looking thing right now.
Right, and it's not really probability, it's like probability amplitude, right? So
yeah, it's a probability
the same
amplitude.
as the wave function.
Yeah, it's exactly the wave function here that I'm plotting. That's right. So the plus state here, so if you write plus state, which is 0 plus 1, that is actually going to be a superposition of the eigenstates of P. So this state is going to be, again, I hope I have explicitly written it somewhere. God, where the heck is it? Of course, I can't find it now. Never mind. But yeah, so you can, so the plus state is, I think, just sum of P equal to square root of, what was it? What was 2s pi? So it's P equal to 2s square root of pi. And the minus state is P equal to 2s square root of 2s plus 1 square root of pi. I think this is right, but if somebody in the panelists know I've written something wrong, please let me know. But yeah, so these, the plus and minus states now become eigenstates of P. Okay. So now what is this crazy looking state and why do I care about it? Well, it turns out that the original GKP code word is defined using, is defined for correcting small displacement errors. Up till now, I told you that the errors happening in the cavity are single photon loss, 2 photon loss, photon gain, you know, those frequency fluctuations that I'm talking about. But all of a sudden, I'm telling you, no, I have a bosonic code and which is designed for small displacement errors, meaning that Mi here is going to be some displacement by some amount Xi. What is this game I'm playing? Well, it's just that it turns out that displacements are good bases, also form a complete basis. So any error you can basically write as a superposition of displacement errors. So yes, I can write single photon loss as displacement errors. I can write 2 photon loss as displacement errors. Anything, any operator in terms of A and A daggers, I can decompose it into some displacement errors. And this was sort of the intuition when they designed this code. And I will come back again to the point of the physicality of modeling noise as small displacement errors. I'll come back to that point. Right, so this code is designed for correcting small displacement errors. So I want to prove to you that all the error correction criteria are going to be satisfied under small displacement errors. And this is actually very easy to see. any displacement error you can actually write as, sorry, just give me 1 second. Just want to make sure I get all my square root 2's right. Yes, so the displacement operator as we defined, this was XA dagger minus X star A. This can be written as, so if I write X equal to U plus IV, X is a complex number, I can write it as real plus I times another real number. This is equal to e to the IUV, e to the minus IU square root of 2P, e to the IV square root of 2Q. This is just some math wizardry we have done, and I can exactly transform this guy into this guy, where now P and Q are your momentum and position operators. Okay, and now so we have to show that your GKP states satisfy the error correction criteria, so that this guy and these guys are same, independent of I's and J's. Oh, 1. And then 0 mi dagger mj, 1 is equal to 0. Okay. Now this it's very easy to see that these conditions are going to be satisfied. I'm going to give you an intuitive understanding with exact GKP states, and then we're going to come back to what happens when I have approximate GKP states. So in the exact GKP states, suppose I have an displacement. So mi is displacement by xi, mj is displacement by xj, mi dagger mj is just d dagger xi d xj, and this is essentially just d of minus xi plus xj with some phase, which I don't care about, and for this part I don't care about the phase, and this is essentially just displacement by some I don't know, y, some other displacement y, right? So and now, sorry, go ahead.
So quickly for these MJs, are they normalized in some way such that there's a completeness relation? And
yeah. So we didn't go through that, but yeah, you can integrate it out, and you can show that the completeness relation is valid.
And you're just being fast and loose with the normalization.
I'm just being fast and loose right now. But yes, the displacement operators, we can normalize them. Okay, so now, so basically this is just another displacement operator. So now basically, in effect, I want to show that this guy is, I want to find out if and when this condition, for example, can be satisfied or not. Now, again, I can write this guy as some, e to the minus IU square root of 2P, e to the IV square root of 2Q. You see that 1 and 0s are the eigenstates of the Q operator. So, okay, so let's look at the one state. So I have, this is 0, this is say the one state, and then I have sorry, this is a logical 0 state, and logical 0 state, and the logical 1 state is somewhere here. Okay, let me just draw straight lines like this. Okay, so now say I applied this guy onto the 1 state, then some of these states are going to pick up some phases. So some of these states are going to go, the amplitudes are going to get, say, negative or some other phase, right? So something like this. Yeah. Okay, maybe some of them pick up some phases because of here. This guy, okay? Some of these peaks pick up some phases. Now, what does this guy do? Well, e to the IP acting on an eigenstate of Q just displaces the eigenstate of Q. Again, you need to have a little bit of quantum optics for this to happen, but again, if you do the math in the pre-reading paper, you'll see that this is true. Basically, so say the blue ones are the eigenstates of Q equal to Q naught. If I apply e to the minus IU square root of 2P to it, this just becomes Q equal to Q naught minus I U square root of 2, something like that. Right, so it just moves around. It just displaces it. So this guy just adds phases to the peaks. This guy, on the other hand, displaces or shifts the peak around. So some of the peaks, some of the blue peaks then, say move like this. Okay, they'll be like, they move a little bit. But you see that if they don't move too much, they're going to still be orthogonal to the 0 state. Right? What do I mean by they don't move too much? Well, they basically can't move more than half of the difference, half of the distance between two of the peaks. So this guy is 2 square root of pi. So this guy, so they can move 2 square root of pi no, sorry, this guy is square root of pi, so they can move square root of pi by 2. So basically, as long as the shift is by u square root of 2, u square root of 2 has to be smaller than square root of pi by 2 for this error correction criteria to be satisfied. Okay, basically the displacements have to be smaller than square root of pi by 2. And everything is fine. You'll still be able to error correct. Similarly, now for the no distortion condition, you basically just look at orthogonality of the plus and minus states. It's the same thing. The no distortion condition is basically the orthogonality condition for an orthogonal basis states. So if you look at the plus state and minus state, they are the eigenstates of P operator. So you can look at the distribution in P space. So one of the states will be centered at P equal to 0, P equal to 2 square root of pi, and so on. And then the other state will be centered at this guy here, this guy here, this guy here, this guy here. In that case, this first guy will only add phases. The second guy is going to displace you. But as long as the displacement is small, how small? Smaller than square root of pi by 2, you'll still be fine. You'll still be able to do error correction. So the GKP code is designed to correct for errors, the small displacement errors that are smaller than square root of pi over 2. If your displacement errors are smaller than square root of pi over 2, you can correct them using this GKP code. Now, of course, when you have approximate GKP codes, these conditions are only approximately satisfied. Approximate so the approximation gets exponentially better with this factor delta I had, this guy here. So the approximation gets better as e to the minus delta, sorry, e to the 1 minus e to the minus delta square or something like that, where if delta is 0, that means I have the exact code words, then I'll always have the error correction criteria satisfied. If the displacements are smaller than square root of pi over 2, if not, then they're approximately satisfied. And if delta is small enough, that approximation is good enough. So you can correct for a lot of the errors, but not all of them. So the bigger the GKP code you make, that is the smaller delta you get, the more errors you'll be able to correct. The smaller delta you have, because the error correction criteria will only be approximately satisfied, you'll only be able to correct for some errors, and you won't be able to correct for other errors. So you'll be able to correct for fewer errors in that sense. Okay, this is very confusing, I understand. I'll wait for a second and take questions.
There's none for now.
Okay, I feel like the reason there's no question is because you guys are like, what the heck is going on here? And I totally understand.
Okay, we got one.
Good, one question, good.
So displacement in Q is analogous to a phase flip error, and displacement in P is analogous to a bit flip error for the logical 0 and 1 GKP states, question mark.
The displacement in P is like X error, and the displacement in Q is like phase flip Z error. Yes, I believe that's correct.
Another one is the main motivation for using GKP sum over Fock states over working just with Fock states is to detect more than bit flips like phase flips.
There's no reason for it. It's a different code. The nice thing about the GKP code, and I'll get to that later, compared to so up till now you've looked at binomial code. The nice thing about the GKP code is that it's the logical operations. Like if I want to do a C0 between two GKP states, or I want to do a Hadamard gate on the GKP state, or something like that, it is just easier to do those gates. There's a concept of fault-tolerant gates in the GKP states. There is no equivalent concept of fault-tolerant gates in the binomial code. That doesn't mean to say that their binomial codes are bad. It's just that the research is still going on, and we don't really have a full path to how we're actually going to make everything work in a binomial code, whereas we have that path in the GKP code case. For me, that's the only reason to work with GKP states. For example, in the GKP states, as I said, in the binomial case, when you wanted to recover for errors, you had to do some unitary, and the unitary was just so complicated that I didn't even want to write it. I don't even can intuitively explain to you how the heck are you going to do that in unitary. Whereas in the GKP state, your error detection circuit basically detects how much you have displaced, how much did you move away from this, 2 square root of pi thingy, how much far away did you move from that? And once you have it, then you just apply an opposite displacement. Then you just apply, suppose this was the error, right? Say you moved about delta, or let's use a different small delta. If you're able to measure that you moved by this delta, you just need to apply a displacement back by delta. So you just need to apply minus delta A dagger plus A or something like that. Oh, sorry, you need to apply displacement of minus delta, which is e to the minus I delta A dagger minus. Okay, I'm messing up i's or not, but something you need to apply this guy in one case. This is a unitary, and this can be easily achieved by applying a single photon drive or a microwave drive to your oscillator. So all you need is a Hamiltonian, which looks like this. So if you have a microwave cavity, you have a pin which you have some sort of a pin, and you apply like an actual microwave pulse on it, and that microwave pulse actually creates this Hamiltonian. So you just evolve. Sorry, you need this guy here. So you just evolve your oscillator for a time GT equal to delta, and then you will correct for your displacements. This is it. This is it. In case of binomial codes, it's not such a simple operation, unfortunately. That's the problem.
But then, Shruti, the next question then is, but to measure delta, you need a nonlinear qubit, question mark?
Not directly, no. So again, I'm going to cover how you actually measure delta in just a second. So explicitly, the only place where you need nonlinearity for a GKP code is for state preparation. How the heck are you going to prepare this superposition of displaced squeeze states? It's just unimaginable. And this is why it took almost 2 decades for the first experiments to come out to actually make the GKP state. Once you have the GKP states prepared, the next steps don't actually require any nonlinear element, don't require a qubit. Put an asterisk on top of that, and we can discuss what that asterisk means later. So that's the only place you need it. Now, how do you detect, how do you measure whether what is the displacement that you had? Remember, I told you that, let me first tell you a destructive way to measure this delta, and then I'll give you a Steen error correction circuit, which uses a C0 gate between two GKP cavities and a destructive measurement of one of the GKP states for error correction. I'm going to give that to you, just bear with me. So what you do is, let me first give you the circuit. So suppose I have this GKP state, which has some errors in it. And I'm going to look at my circuit here just to make sure I'm not going to make any errors, because it's a little bit hard to explain. There you go. Yeah. So this state has some errors on it. So this has some displacement along of Q, or some displacement like this, or superposition of the displacement. Doesn't matter. I'm just writing it for clarity, just writing it as two separate things for now. Then what I do is, suppose I want to measure what was V, right? I want to measure what is V. That is, what is the displacement along P quadrature. Then what I do is, I do a C0 gate between this guy and an ancilla GKP state prepared in the 0 state. So this is the ancilla GKP state. Now this is not a regular qubit ancilla. This is still a cavity. Okay, this is still a cavity. It's a GKP state in a cavity. And you do a C0 gate between those two. Because of the C0 gate, what is the C0 gate, if you guys remember? I'm sure Austin Fowler might have done this. C0 gate is basically, if the control qubit is in the, if control state is plus an eigenstate of Z, don't do anything to the target. Otherwise, you do an X to the target. Okay, so we are basically doing this gate between two cavities. And in order to do this gate between two cavities, the Hamiltonian that I require is proportional to A dagger plus A, tensor A dagger minus A. So this is like a Q tensor P type of interaction between the two cavities. Okay, once I do this, again, you can do the math. It's just commutation of things through displacements. If you just sit down with it for 10 minutes, it'll be like very trivial to see it. So if you do this, then basically what happens is that the state that comes out is this state basically inherits the displacement from this guy. So this just becomes e to the I V square root of 2Q here. So this basically, this guy gets passed on to this guy over here. Of course, it remains here as well. So a V becomes a V up, a V on the data GKP state becomes V on the data GKP state, and a V on the ancilla GKP state. Now what I do is I do a homodyne measurement. I measure P. What is a homodyne measurement doing? The homodyne measurement is just seeing, is measuring the eigenvalues of P and eigenvalues of Q. You can do a homodyne measurement to measure eigenvalue of P, and you can do a homodyne measurement to measure an eigenvalue of Q. When you do a homodyne measurement and measure an eigenvalue of P, if basically you're basically measuring where you are, where you in this grid that you were, it's basically measuring, are you at any of these points? Are you at 0, square root of 2 square root of pi, 3 square root of pi? Are you there, or are you delta away from it? So if you do a homodyne measurement, and if the homodyne measurement result, sorry, this is 4 square root of pi. If the homodyne measurement result was 2 square root of pi, that means V was 0 and there was no error. If you did a homodyne measurement and you measured like 2 square root of pi plus delta, then you know that there was a delta error on this guy and you can go back and correct it. Now, in doing the homodyne measurement, you have completely destroyed the GKP state. So you cannot reuse this cavity anymore. You have to re-prepare the cavity. If you want to do further error correction, you have to re-prepare the cavity in a new GKP state, and then do the C0 gate, and then again measure the momentum, the homodyne measurement on the new ancilla.
A question, Shruti?
Yeah.
Is the C0 symbol flipped? Why does the control bit change?
Why does the control bits change? I don't think the C0 is flipped. So the naught is, what was naught? The naught is, let's go back to our operators. Yeah, so the X operator is displacement by alpha. Alpha is square root of pi over 2. So just a second. So the naught is, yeah, so naught is e to the square root of pi over 2 a dagger minus a. So this is basically e to the I 2 pi p or something like that. So wait, what was the question? What is flipped? Why do I still get this out?
I think
Why
the
does
confusion is why the control bit changes. Normally you
Oh,
intuit with
oh.
a two-level system that the control bit is 0 or 1 and the result on the other qubit is something or not something. But why is there like propagation to the control bit, let's say?
Because this thing doesn't commute. You're just doing you just, so in a regular qubit system, say you were measuring the in your surface code, you have your four data qubits and you have ancilla at the center. You do a control NOT gate between the data qubits and the ancilla at the center. The control NOT transfers the errors on the data qubit, maps those errors onto the ancilla qubit. This is exactly what is happening here. So here you're basically, the unitary that this C0 is actually doing is something like, it's not exactly that, but it's something like e to the I p on the data qubit tensor q on the ancilla. Okay, because so here the data qubit has some error, which is e to the I v square root of 2 q. If you do the commutation relationships through, you will see that this will be equivalent to, again, do the commutation relations properly. I might be missing some terms, but this will be something like VQ2, this, and then the gate is happening perfectly. Something to this effect. So in my notes, I do the full like math to show that this happens, but it's just because you do not commute Q through. Q doesn't commute with P. So when you properly do the commutation relationships on P's and Q's, you will see that you get an extra thing here on your ancilla. You get an extra displacement on your ancilla, which then you measure, because the displacement on the ancilla is the same as the displacement on your code word, and that's what you are able to detect and then correct.
This next one is also related to C0. What does displacement along P mean if the state is squeezed along Q?
So if you have something like this to a Q, if it's an eigenstate of Q, then this is just Q equal to Q naught plus X or something like that. Is that the question? Can you repeat the question, Shraddha?
What does a displacement along P mean if the state is squeezed along Q?
Yeah, so this is it. When I say state is squeezed along Q, I mean it's an eigenstate of the Q operator. Then you apply e to the IP to it. Q is not the eigenstate of P, so therefore, again, you can do the math and you can numerically prove that, or analytically prove that this is what happens.
And then
This
the
P is
corollary,
just, yeah, Sorry.
I guess the question I think is also about the corollary to that. What does it mean to have an e to the I x q on a q eigenstate?
Oh yeah, so right. Okay, so e to the x q on a q eigenstate is just picking up a phase, right? Because q is an eigenstate of, so this is an eigenstate of the q operator, so you just pick up a phase, whereas here you actually displace the state because of the way the commutation relationships work.
Thanks.
So in this case, you see, again, I apologize. This is, you need to know your commutation relationships to believe that this happens. And this is why there was a pre-reading notes. But again, I'm going to send typed up notes so that you don't hate my handwriting and then never read the notes. You can do the commutation relationships properly, and you'll see that if you do a C naught like this, this displacement error, this shift error is basically transferred to this qubit. And similarly, if you did the C naught the other way, so if you want to measure what this displacement was, if you wanted to measure what this U was, then what you do is you initialize the ancilla in the plus GKP state. And then you do a C naught this way between the two. So if you had this guy here, then this will get transferred to e to the I u squared of 2p here. Again, because of the commutation relationships. And now again, you measure the ancilla. This time you do a homodyne measurement of the Q quadrature of the ancilla. And depending on, how far away it was from a multiple of 2 square root of pi, there was an error or not, and then you can go back and fix it. Okay, I'm going to wait for 2 seconds if there are more questions.
And right now?
This is super. So this is one way to. So this is how you imprint. So you could basically use an encoded ancilla to prevent that back action that I was talking about before. But here the encoding is in another GKP state. And you only require a Hamiltonian interaction like this between them. So you only need like a Q tensor P type interaction between them. Sorry, go ahead.
There's a question in a broader sense. Can you elaborate on your comment on fault tolerance in the GKP code? Is it just that correction is simpler?
No, I'm not sure when I made that comment and in what sense. But here, for example, the gates are, the C naught gate is fault tolerant between these two GKP states, in the sense that, you're not with this Hamiltonian, you're not introducing an uncorrectable error in your system.
I think this came up when you were comparing GKP and binomial code as to why we should choose GKP code over binomial code.
I see. Okay, yeah. So in the GKP code, because there's this path to do error correction, there are several reasons why you should pick GKP codes. One is that you can do this kind of error correction, which doesn't explicitly require an ancilla. And I'm going to come back to that point again. It doesn't explicitly require a qubit, like a regular transmon like ancilla, for example. The other thing is that the gates, you can do universal gate sets here. You can do Hadamard, you can do C naught, and these gates are fault tolerant. You can for example, the C naught here, you can if you get this Hamiltonian, this is not a hard Hamiltonian to generate. If it belongs to a category of Gaussian interactions, which are sort of easier interactions to have. And with this Hamiltonian, you can have a fault tolerant C naught in the sense that it's not introducing uncorrectable errors in your system. Okay, so you will so as long as so unlike the other case when a bit flip error in the ancilla was introducing this high weight error, which there was no way for you to correct. This doesn't happen here. So this is the nice property about it. With binomial codes, I don't know how to do fault tolerant gates. I mean, I can write down the Hamiltonian that I would require for it, but it's just super complicated, and I don't know how to implement those Hamiltonians without actually requiring a regular transmon-like ancilla. So now I'm saying it doesn't explicitly require an ancilla, and what do I mean by that? Well, explicitly, because firstly, I still need to prepare the GKP state. So in order to prepare the GKP state, I still need a transmon-like ancilla to prepare the GKP state. So that is being hidden under the rug. The other thing is that this Q times P interaction, how do you actually generate this interaction? How do you get an interaction which looks like this between two oscillators? It turns out that you need at least a third order nonlinearity. You don't need a transmon. You can get away with using something which is not a transmon, which has a third order nonlinearity to actually implement this interaction. So again, we need some nonlinearity to implement this. So in practice, the external nonlinearities that you're adding into your system, the back action from that will limit the performance of the GKP code at the end of the day. It will happen. You see, because as I said, you need a transmon, for example, to prepare the GKP state. Again, the same X error in the transmon is going to backpropagate onto your system. That X error is not small displacement error that happens. That X error the error introduced by the X errors on the transmon actually gives a large displacement error which is greater than square root of pi over 2, which is uncorrectable. And that's the problem. So eventually, at the end of the day, the errors, how good of a GKP qubit you can make, again, depends on that bad element, that transmon that we did not want to use to begin with. But then again, you would ask me, what is the point then? Well, the point is that I will correct for most likely errors. Of course, there's going to be some residual errors, and I'm going to concatenate this code to GKP code to a surface code to actually correct for the remaining errors. For example, the errors that are coming in from the transmon, or the errors that are coming in from some other like, not distortion, some other basically there are things that can make your harmonic oscillator not harmonic anymore. It can have some anharmonicities, and so anything that spoils that will cause a problem. And so those small residual errors that are going to be remaining in your system can be corrected by the surface code that comes on top of the GKP code. I'm going to just wait for a second to see if there are any questions. To me, at least there's a path in GKP codes to actually, if I have this Hamiltonian, then I could do this or that. In the binomial codes, it's just absolutely crazy the things I need to do to make it work. But that doesn't mean that they're bad. It just means that it's an opportunity for new research. So if you guys are interested, please find me better gates for binomial codes. Please, I need that.
You've got a live question now. Could you briefly explain why you need the nonlinearity to do this ADAG plus A? I think that's a tensor product in text, ADAG minus A thing. It just seems like two drives with two different phases.
Two drives with two different phases would give me not this Hamiltonian. It'll give me A dagger plus A tensor I plus A dagger plus I tensor A dagger minus A. So if I have two cavities, and if I put that pin that I was talking about and put two drives there, it's just, there's no coupling, right? There's no coupling between the two. It's just independent drives on the two systems. So basically, to make them talk to each other, to make them couple to each other, I need something in the middle here. I need something in the middle there to get this interaction. And I very specifically drew this symbol, which looks like this spirally thing, which is actually something called as a snail, which Nick works on. And you can use a snail to, for example, introduce this coupling. Hopefully this, so at least for this coupling, there's no like even there's no like bit flips in the snail that can propagate back. So at least for this case, that the bad errors would not happen, and you'll be able to sort of get a fault tolerant CNOT gate. So that's good. But at the end of the day, you still need to prepare the states, and you need a regular transmon qubit for that, in which you're going to have bit flips, and then you're basically lost. I mean, not completely lost, but I mean, you're limited by what you can do with the transmon. You could replace the transmon with, again, flag fault tolerance. You can replace the transmon with bias, noise, and Scylla. And, all of those tricks are valid, and people are trying to build those. Alec, you can talk to Alec about it too. So yeah, you can use the noise, bias, and Scylla to prevent that back propagation of bad errors into the system. So there is a path. There's a more clear path towards fault tolerance, let's say. Okay, I'm going to stop here. We can do more. We have like a few minutes before we have to go to the social discussion section. We can take a break, whatever you need to do. I'll be here if there are more questions. Before everybody leaves, I want to introduce you the folks here who you can talk to during your social discussion. So Nick and Shraddha, I already introduced to you. We also have Chris Wang, who is a experimentalist, is a grad student in Rob Sholko's lab, and he does a lot of actually algorithms with bosonic qubits. So if you're bored of thinking about error correction, want to talk about algorithms, definitely talk to him. We have Connor, who is also a grad student here. He's Liang Jiang's student. He's a theorist, also expert in these bosonic systems. And we have Alec, who is the GKP guy. As you can see, he's probably in the lab wearing his mask. So,
Shruti, you now have a question waiting from before, which actually had been brought up a little bit earlier, which is to ask a little bit of physical intuition about these sort of cavities that you've been talking about, because you say it's hardware efficient in theory, but could you give an example how really to implement it in hardware to really give folks some physical intuition? Yeah,
let me actually, this is what I wanted to show you guys a figure, but I was unable to transport it on my iPad. So let me stop the sharing on iPad, and I'm gonna share on my computer. Okay, so let me just show you guys that figure on my computer, and just 1 second. Okay. Also, this paper is not available right now, but it will be very soon. We just wrote a perspective article on GKP state. So here, this is the figure I wanted to share. Okay, so this figure is not available online. This paper has not been published yet. But if you wanted to do, say, build a surface code with these 3D GKP qubits, this is what it would look like, right? So I'm going to explain everything. Just bear with me for a second. So in the surface code, you have qubits. You have data qubits on a square lattice. So these orange 3D cavities are those data qubits. The blue cavities, the blue 3D cavities, are the ancilla qubits for the GKP surface code. For the surface code. Remember, Austin Fowler might have told you this. You have a square lattice with data qubits. At each face, you put a ancilla, and you use that ancilla to measure these 4-body XX and ZZ operators to measure the stabilizers for the surface code. So this is what this blue guy is doing. You put some coupler, like the snail thingy that I was telling you about. You put some couplers between these data cavities, these couplers between your data cavities and your ancilla cavities to do the C0 gate, which effectively then will be used to measure the XXXX and ZZZZ stabilizers of your surface code. Now, what is this green cavity here? This green cavity is going to measure the stabilizers of the GKP code, what I told you just about. Just, I told you this, I gave you the circuit where I do the C0 gate between the GKP state and an ancilla cavity, and then you read out the ancilla cavity, do a homodyne measurement on the ancilla cavity to determine if there was an error or not. This is what these green cavities are doing. So you have 2 layers of protection. One layer of protection comes from this, just doing error correction directly on the data qubits using this green cavity. But that error correction circuit, because of these extra couplers that you're going to add, because of transmons or whatever it is, you're going to have some remaining errors, which you won't be able to correct at this first GKP level. To correct for those errors, then you measure these 4-body operators, XXXX and ZZZZ, at the level of surface code to correct for everything else that remains. So this is what it will look like. Now, what are these? So these are the way we imagined it. Well, actually, Nick and Alec helped me, visualizing this picture. So basically, have your 3D aluminum cavities. You have these silicon. What was it? Silicon substrates or something? Yeah, these greens are the silicon substrates in between them, and you put your transmon or your SNAVE, whatever it is, you make it on that, and you basically just, this is how it would look like if you were able to build it. As I said, you don't have to do this in 3D. You can have a high Q 2D cavity in which everything is going to be in plane. There's no reason to do 3D. If you wanted to do 3D, this is what it would. This is one way it could look like. I wonder if that answered the question. At the end of the day, we need it for any bosonic qubit. At the end of the day, we need a surface code or something on top.
Yeah, so maybe the follow-up question to this is more at the like physical level, like sort of like what are the, like you said aluminum, but like instead of a schematic, what like physically what are we talking about? Like, so you said chips, but this sort of dot is like it's like a block of aluminum.
I see. Nick, do you have like a paper I can open actually to show the? Oh, there you go. Chris has it. Chris, do you want to?
Sorry, yeah. So if you let me take a moment and just take the screws off, I can.
Do you want to like? Yeah. Okay.
If you can pin my screen, I suppose.
Yeah.
So in Shruti's diagram, you saw all these, circles that were the post cavities. And so in real life, I mean, this is sort of a sense of scale. This is my face. So if you look in there, that would be an example of a scale of one of these 3-dimensional post cavities as we envision them today. And so you're looking at, few millimeters in diameter, approaching, I guess, in this case, maybe almost a centimeter. In this case, there are 2 of these cavities. And what you can also see is that there are these tunnels on the side that support these, these are the sapphire wafers with the nonlinear elements that Shruti described on them, which will physically just, kind of slot in to interface with the cavity. So for a sense of scale, this is 2 bosonic cavities with 3 nonlinear elements. But yeah, again, it doesn't have to be this size, but currently this is the scale we're talking about.
And Chris, can you point out the probes or the ways we get the signals in?
Right, and so all around here, again, sorry, this is sort of an old device that's really, as you can see, just kind of, torn apart. But everywhere along this interface, you'll see these sort of connections where we'll eventually hook up a transmission line. This thing gets bolted to the base of a dilution refrigerator, and these transmission lines eventually send signals from a room temperature microwave electronics down to the sample and then back up. And so you'll notice here for 2 cavities and 3 qubits, there are 1, 2, 3, 4, 5, 6, 7, 8. I guess in this case, eight control lines. And so that's also sort of another consideration once you scale up, especially in 2D, is how you can get all of those control signals in and out.
So Chris, you also, maybe you don't have to show this, but here, just to be fair, you're just showing 2 cavities, but you also have a chip with like 9, like a 3x3, like almost like looks like a surface code patch of 3x3 cavities.
This is true. It's in the other room.
Don't get it.
Yeah, I don't know if I'm allowed to show that, but also, yeah, that. So you can just imagine this kind of thing just with more, right? Like you can tile this into technically any 2D grid you want, and then it's sort of about how do you get all of these guys in, and so that's sort of an engineering problem. How do you can interface from the top, the bottom, the side, and then now you're getting into an optimization landscape that requires a lot of careful microwave engineering to optimize. But in principle, you can literally just envision this and tile these in X and Y to create a surface code.
And I guess on top of that, redirecting to Shruti, you've got a question that says, I think you mentioned this already, but the motivation for bosonic error correction is that you can use less physical qubits, but it seems that you need additional qubits for each GKP component. So
absolutely, yeah. So the hope is that we need total fewer components. Absolutely, we don't. So sorry, let me share the screen again. So yes, so basically, when I do a resource count, I have to count how many cavities I'm using and how many of these extra couplers and extra qubits I'm using. So the idea is that I need fewer data qubits to fewer of these orange things, which means I'll need fewer of the blue things, which means I'll need fewer of the green things, and which will mean I need fewer of these, couplers together. So we have to optimize. So to be really hardware efficient, we have to make sure we count every piece of the resource that goes in there, and total resource cost has to be lower than if you were, to build this thing, just, build a surface code with transmons, for example. For sure, that is the case. There is some work recently by Barbara Terrell and also Kyunju Noah and Chris Chamberlain and others who have actually done some calculations on building a surface code with GKP qubits. I believe that in that, even if you count the extra resources that you're going to need, you'll still require fewer total components than just with the transmon, based regular surface code. However, the savings is not that much. I think that so again, this is a very active area of research. For example, we are working on how to even further reduce that extra hardware cost. This is only one way you can do this surface code. There's another much more hardware efficient way to do the surface code. It's a less studied area where you actually don't use GKPs as ancillas. You directly use qubits, like you use bias noise qubits, for example, as ancillas. And that should give you much more resource efficiency. The problem is that it's a little bit tricky to properly model the noise channel. And that is a hard part, and that's what we're trying to do. So it's a very, very active area of research. This is why I love it, because we don't know all the answers yet.
So along those lines, why you love it, and then what motivated you to pursue bosonic codes as opposed to, say, other error correction schemes? Is it particularly compatible with hardware, or?
Well, I mean, so my training is in quantum optics. I'm a quantum optics theorist by training. And when I first saw you could measure Wigner functions and all these make these crazy non-classical states in circuit QED, I was like, I have to be there. Like, this is amazing. Like, optics people, like to measure Wigner functions with the quality that happens in circuit QED is just amazing. Like it's just awesome. So therefore I sort of, moved to these things, and, I was looking at all these amazing bosonic error correction stuff coming out of Yale. And I just wanted to know, like, what kept me up at night was like, why are these qubits, why is this better than transmons? Why should anybody actually use this rather than transmons? And my whole research has been trying to answer this question. Why is this better than transmons? We have the answers. We have certain situations. The Kirk-Cat qubit, which, for example, I think is really better than transmons. But I did not talk about that today. It's just a little bit more complex. But anyways, yeah. So we for certain cases we definitely have a path forward, and we know why it's better and how much hardware efficiency we can get. But I don't think that's just one system. I think that GKP qubits are awesome. I think binomial qubits are awesome, and we just need to find new things for me to do. It gives me an opportunity to be creative. Is I guess my point.